Good morning, everyone. Welcome to our Emerging Contaminants Forum. Appreciate everyone who's signed up, and big thank you to the speakers for the day. I want to thank Terry Obel over at Bureau Veritas Lab and Lindsay Patterson and Matt Cody over at SLR Consulting for helping me when I was brainstorming this idea and trying to think of some topics and then taking a look at the agenda when I had it finalized. So I appreciate your help, both of you. The recordings will be available at the end of the presentation. Watch your emails for the details. Hopefully tonight or tomorrow morning I'll have them out. Our free webinar series has returned. We have a couple already booked for later this month, so you can check those out. And then REMTech is about 3 weeks away. Encourage everyone to sign up for the virtual version. There's about 60 talks over the couple days. Enjoy the day. On your control panel on the side, you'll see a tab that says handouts. There's a handout in there that's a PDF of all the presenters' bios and a little bit about their presentations. So you can download it, look at it, print it off, and go from there. So we have a small addition to the agenda. We're going to just a short, few-minute talk. Sean Samborski from CORE Canada and also a member of the ESAA Board of Directors just has a short presentation. He's working on a study. He's going to give us some more information about PFAS quantification in landfill leachate. So I'm just going to turn it over to Sean.
Good, excellent. Thanks, Joe. Oh, I'm just going to hit show my. Good. So the presentation consists entirely of this slide, but what I want to chat about, I apologize if you hear my stomping 3-year-old upstairs. We're living under a 3-year-old, or I guess under the regime of a 3-year-old. And so if you get noise in the background, I apologize for that. Thanks, Joe, and thanks to ESAA for having me in. It looks like this is kind of a receptive crowd given the fact that there's 3 presentations on PFAS. And so what we are doing or trying to accomplish is our friends at Stantec, Core Environmental Consulting, and the U of A here in Edmonton are doing a Canada-wide study of PFAS in landfill leachate. And essentially, we want your leachate if you own or operate a landfill facility anywhere in Canada. As everybody, I think probably, or many people on this webinar will know, a landfill makes a particularly good study area because it tends to concentrate PFAS, both from consumer products as well as soil from remedial projects, intentionally or unintentionally having brought PFAS to landfill facilities. So the goal of the study is essentially, presence, absence, and prevalence and concentrations of PFAS in landfill leachate. And then given that information and quantification of PFAS compounds in landfill leachate, what's the best way to remediate what is usually a pretty complex medium. So the study itself, there's a web link on the screen that has a much more fulsome document regarding the aims of the study, as well as a link on how to participate. The study is blind, so information about the participating facilities will not be presented or available. It's at no cost, so the funding is coming from sources outside the landfill facilities themselves. So again, if you want to email me or call me with any questions, I can certainly get those to the right people if I can to answer them. And if you want to participate, or if you want to refer someone to participate, that link below at core-canada.com /PFAS-study is the link, and that will take you to a SurveyMonkey survey where you can provide us a little bit more information about your landfill facility, and we will contact you. So thanks very much, Joe, and I appreciate the time.
Thanks, Sean. Anybody have any questions for Sean before we move on? No. Sean, I will put you in touch with Rita. She mentioned someone from Environment Canada is doing a study as well, so there might be some synergies there, so I'll put you in touch. Okay, our next presentation, our first presentation, PFAS in Canada, Federal Perspective. We have Marita Moraz from Environment and Climate Change Canada out in Halifax. They survived the storm, thankfully, didn't lose power. And Darcy Longpre with Health Canada. So I'm going to switch it over to them. And at the end, as always with our presentations, we'll do the questions at the end and we'll come back online for the presentations. Give me a second.
Can you see it, Joe?
Yeah, you just need to do, yeah. Perfect, sounds good, looks good.
Oh, did I mess it up again?
Oh, looks good, looks good.
Okay. Excellent. I'm just going to. Okay, so I will start. Good morning, everyone. Thanks to Joe and members of the Environmental Services Association for inviting Darcy and I to speak to you today. We're going to share with you what we've learned collectively over the last 15 years as we've dealt with federal contaminated sites that have PFAS contamination on them. So after a quick introduction to these compounds, we're going to focus our presentation on the evolution of perfluoroalkyl substances, or PFAS, management at generally in Canada, but more specifically on contaminated sites, and how we built up our collective expertise related to analytical issues, sampling protocols, guidelines development, contaminated site management, some remediation technologies and some of the work we've been doing in that regard, and also some of the collaborative opportunities that working with this class of chemicals has presented, and some of our closing thoughts and some of our ongoing challenges that we are still facing. So PFAS are a family of man-made chemicals. They're all anthropogenic, found in a wide range of products used by consumers and the industry. There are over 5,000 PFAS compounds, but the most widely studied to date are perfluorooctane sulfonate, PFOS, and perfluorooctanoic acid, or PFOA. So up in this corner is the PFOS molecule, and you can see the carbon-fluorine bond. That's one of the most strongest chemical bonds on the periodic table, and as a result of this very strong bond, these compounds are very persistent, non-amenable to naturally breaking down, and very stable. So as a result, these properties, they're very widespread in the environment. PFAS are now ubiquitous. They're detectable concentrations in humans and ecological receptors all over the world. And there's the potential for very long dissolved plume in the groundwater, and also long-range transport in the air, especially with the shorter chain PFAS compounds that have been developed over the last couple of years. To date, there's limited remedial options available in Canada in terms of full-scale remedial options. Thermal technologies such as high-temperature incineration and sequestering type technologies like the use of activated carbon for groundwater treatment are the most common. However, we are piloting some promising technologies, and they're likely to lead to additional options for treatment going forward. In terms of sources for PFOS and PFOA in Canada, there's no known production ever of PFOS or PFOA in Canada. However, we imported these chemicals as fluoropolymers until they were banned in 2008 for PFOS and in 2016 for PFOA. So they were brought into Canada and then used in manufacturing processes in the production of textiles, paper manufacturing. So they can be found in aqueous film forming foam, papers, clothing such as our Gore-Tex carpet manufacturing, carpet care products, and oil water repellents. So the releases in Canada are typically the result of wastewater effluent, consumer and industrial manufactured items, deliberate discharge, such as at crash sites where the AFFF has been applied, and also fire training exercises at many airports. Also, long-range transport is an issue for the northern communities and receptors. So we wouldn't be a regulatory agency if we didn't present some regulatory highlights. There's not a lot of regulations with respect to PFAS compounds. In 2006, the first PFAS screening assessment report was published, and that was under the Canadian Environmental Protection Act, and that was an ecological and human health risk assessment. It was deemed that PFAS is persistent, bioaccumulative, and was having a potentially negative effect on the environment. So when that under SEPA, those characteristics are deemed of a particular compound, then the government is mandated to do something about it. So as a result, in 2008, the PFAS and its salts and certain other compounds regulations was published to prohibit the manufacture, use, sale, and offer for sale or import of PFAS into Canada. In 2009, PFAS was added to the SEPA environment or virtual elimination list, which has kind of bumped it up further in terms of our goal to virtually eliminate this compound from the environment. Coincidentally, it was also added to the Stockholm Convention, which is an international convention to control persistent organic pollutants. 2012, similar to the PFAS screening assessment, the PFOA assessment report was released, and also a report on long-chain perfluorocarboxylic acids. Those assessment reports were released. In 2016, the prohibition of certain toxic substances regulations added both PFAS, PFOA, and these long-chain compounds to these regulations. As a result, the 2008 regulations were for PFAS were repealed, but they're all captured under that one regulation now. Since 2018, there's been consideration to further restrict these compounds under these regulations, and there was a document released in 2018, and we expect that these amendments are going to be take place in 21, 22. There will be a public comment period, so if you're interested, it will certainly be available to the public to comment before it becomes law. But for example, right now, you can have a residual PFAS concentration in AFFF of 10 parts per million. So now they're looking at eliminating that residual. So in terms of contaminated sites in Canada, most fall under two camps, so to speak. Federal sites are dealt with under the federal government, and we've been working on these federal PFAS sites since about, like I said, about 2010 in a really active way. We've identified several sources, including emergency response sites and fire training areas at airports, military installations, and fire research facilities. There are some other potential sites, landfills that are present on larger bases. For example, we haven't gone down that road. Maybe it's something that Sean would be interested in getting some samples. But there are other sources that we need to look at later. Under the provincial jurisdiction, they have potential PFAS sources as well, landfills, biosolid applications. There's also, like the federal fire training area, there's also college and technical school fire training facilities, fire response, and also smaller regional airports may have fire training areas. So a lot of these sites are being funded under the by the Federal Contaminated Site Action Plan. That initially was a 15-year plan that was in 2005 to 2020, and we spent $4.5 billion assessing or remediating high-risk federal contaminated sites. Because we weren't done, the program has been renewed for another 15 years, so 20 to 2035. And we've got some funding for the first 5 years of $1.6 billion. And this map here in corner just shows you the locations of all the sites. The goal is to reduce risks to human health and the environment, and also to reduce the federal liabilities associated with those. And for further information, there's a website, and I can provide those later. So these kind of breakdowns of the years are a bit artificial, but they do somewhat represent the distinct periods of our PFAS knowledge. So before 2005, we didn't really have a lot of knowledge with respect to PFAS compounds, particularly at contaminated sites. There were research and monitoring activities, which went to the development of the PFAS report that was released in 2006. But in terms of contaminated sites, it wasn't really on our radar. There was no regulations, no guidance, no guidelines, and we weren't really thinking about it in terms of contaminated sites. So then the next few years, there was a bit of a flurry of activity with respect to the federal government overall, in terms of publishing the PFAS document, developing regulations, and near the end of this period, the contaminated sites started to emerge. I still remember in 2010, a base environmental officer called me and said, "Rita, what do you know about PFAS? It's in my groundwater." And I said, "I have no idea." So that kind of started our learning curve, and it was a very steep one for sure. And one of the first things we did was to notice that we did have some sampling lack of knowledge with respect to how to even sample this stuff. So then over the next 5 years after that, we developed guidelines. We developed a interdepartmental working group with stakeholders, particularly DND and Transport Canada. We initiated some research and activities, both in the field and bench scale and in the labs. And we really improved our analytical protocols and our capabilities at this time. So in the last 5 years, we really refined basically what we did in between 2010 and 2015. I'm not used to this animation. So we did additional field trials. We updated and improved the guidance that we had. For example, Health Canada issued 11 screening values for drinking water, and Darcy's going to get into that a little bit later. We hosted a national PFAS contaminated site working group in Halifax. And now kind of going forward, we're looking at updating our regulations, maybe bringing more in, and potentially developing some sort of strategy nationally to deal with these. So now I'm going to go into some of these, a few of these aspects in a little bit more detail for each one. So in terms of analytical issues, we really had limited lab capabilities prior to 2010. There were very few labs that were able to analyze these compounds. We couldn't analyze a lot of them. The QA/QC was a bit questionable sometimes. So one of the first things we did was to look at an interlaboratory trial to identify and try and source out why we were getting some of these inconsistencies between the few labs that were analyzing for PFAS. Then we did round robins to test the effects of sample containers and the difference between having a whole sample or just a 50 ml container, and the difference between subsampling from here and collecting these and analyzing the whole sample. We also were questioning what the filters were doing. So in 2012, it was determined that the nylon filters were introducing bias such that the PFAS compounds were sticking and absorbing to the nylon filters, and not, so therefore what was in the sample was not totally representative of the PFAS. So those were eliminated, and from what I understand, glass filters were used going forward. So Currently, there are more labs, more analytes. There's 25, 30, Terry, you probably would know much better than me, but 25, 30 analytes are pretty common in a PFAS suite now. They're lowering the detection limits, which is good because some of the guidelines that are being developed are in the parts per billion, parts per trillion in some cases. We've got other options such as the TOP assay or the total oxidizable precursor assay, and also the PIGGY assay, which isn't quite as common, but it's the particle-induced gamma ray emission assay. I won't get into all the details about those, but I can give you some more information if you were interested. So I guess the bottom line is what we would do is recommend that you contact the lab ahead of time, where you're going to get the samples analyzed in order to use their prescribed and preferred method of sample collection in terms of the sample container, the sample volume, and handling and storage requirements. We also looked at sampling protocols. At the beginning, back in 2010, when we were doing more large-scale sampling efforts, we put into place a very prescriptive sampling protocol such that you couldn't eat at a fast food restaurant for several days beforehand due to the PFAS on the wrapping paper of fast food sandwiches. They didn't want the site technicians wearing deodorant, or no Gore-Tex, no Teflon in the field. All those kind of things. It was very prescriptive and it was very strict in terms of what we wanted to see in the sampling methodologies. So then in 2013, the Environmental Services Group in the Royal Military College did a study to see if these were very overly prescriptive, and was there any actual cross-contamination going on by using some of these common SOPs or what we would normally use in the field for collecting samples. And it did support that the restrictive protocols were a bit too prescriptive. However, no one's really wanted to back off from those, and those are still in place today in terms of what you can and should use in the field. In 2013, Health Canada developed environmental site guidance. Darcy's going to again talk about that in a few minutes. There was also a study on groundwater sampling methods. They looked at traditional low flow sampling. They looked at up in this corner, Nick has got a hydrosleeve approach and also a traditional baler. And there was good agreement between all three methods. There wasn't a lot of difference, and no stratification within the samples either. So currently, Transport Canada and D&D do have these relatively strict sampling protocols in place, and they require that of their field technicians. The US ITRC have a great set of fact sheets, one of which was just issued in April 2020, and it deals specifically with sampling protocols. So getting into the guidelines, Environment Canada develops what are called the Federal Environmental Quality Guidelines, and they're often developed for several environmental matrices, and they're benchmarks that are used to measure environmental quality. They're used for monitoring, evaluating monitoring results, and also useful in risk management approaches. So not necessarily contaminated sites, but the contaminated sites people adopt these regulations and use them in the field. So these are the Federal Environmental Quality Guidelines for PFAS that were developed following the CCME protocols for surface water, fish tissue concentration. Note that this fish tissue is to protect the health of the fish, but not necessarily the health of the consumers that would eat the fish, and in terms of protecting against bioaccumulation. So this is strictly a toxicity to the fish protective value. There's also wildlife diet concentrations and bird egg residue. There's not a lot of ecotoxicity data available for many other PFAS compounds. There is a Federal Environmental Quality Guideline in development for PFOA. However, once that's been developed, I'm not sure when we will see the next FEQG for a PFAS compound. There's none on the books right now. There is soil and groundwater quality guidelines almost ready for distribution by the CCME. They were posted last year for public review, and they're just finalizing some of the details now. And so we would expect to see them very soon. And BC, actually, on the provincial side, BC is the only province that has guidelines for PFAS and PFOA. Other provinces must depend on these federal guidelines, I'm not sure, but BC does have some numbers. So with Health Canada, I'm now going to turn it over to Darcy to do her thing. Darcy?
Thanks, Rita. I hope everyone can hear me?
Yes, I can hear you.
No.
Yes, we can hear you.
Okay, great. I'm sorry, I'm not able to see the presentation as I present it, so hopefully just interrupt me if people can't follow along, but Rita will change the slides for me. So most of what I'm going to talk about are the human health quality guidelines that are developed at Health Canada. Health Canada does have the mandate to develop guidelines for a variety of media, such as food and air, as well as the water and soil that I'm going to talk about today. I work with the Contaminated Sites Department, and we developed the soil guidelines as well as groundwater quality guidelines more recently. And the drinking water group developed the guidelines for drinking water quality. And both of our departments also work alongside with the federal and territorial jurisdictions to develop guidelines that are nationally applied. So in my group, we work with CCME, the Contaminated Sites Working Group, and with the Drinking Water Quality Group, they work with the Federal, Territorial, Provincial Committee on Drinking Water. So we have developed guidelines that would be for the PFAS, some PFAS that have gone through the Federal, Territorial, Provincial committees, and then we have others that have been developed just in-house at Health Canada. So I'm using the term guideline, but it covers the published guidelines that have been done nationally, those that have been just within Health Canada, those that are interim, those that are final, et cetera, et cetera. But I think everyone knows, and Rita just said, that PFAS is where we're at. Everybody has guidelines for that. For human health, we also have PFOA guidelines, and the other ones are considered somewhat interim. The soil guidelines are not readily available at large. You would have to contact Health Canada, the Contaminated Sites Department, to get those, whereas the drinking water guidelines are available online, as are the guidelines that Rita just presented on the ecological side. We try to collaborate between the soil group and the drinking water group to the extent possible, as well as with other departments, but they don't develop as many guidelines, in order to have the same toxicological evaluation. So we base our guidelines as much as possible on the same TRVs. The soil and groundwater guidelines are always set on toxicology, whereas the drinking water guidelines may also consider things such as treatment technology limits or aesthetic considerations like taste or odor when they're setting their guidelines. Another difference is that the drinking water guidelines are levels that you must attain. They're not regulatory, but the provinces will always have their own regulations that are in line or more restrictive than the federal guidelines. Whereas the soil and groundwater quality guidelines are used mainly for assessment. So site investigations, risk assessments from sites, as well as setting remediation goals. And they are not generally written into legislation, although some territories and provinces can do that. That can have some implications for updating, though. Once it's into law, then it can be take much longer to update those things. If you look at the table here, you can see that the 9 PFAS and the 2 fluorotelomere sulfonates for which the guidelines have been developed. In the second row, you've got all the drinking water guidelines. Some of those are finals, PFAS and PFOA, and others are considered screening values. The same goes for soil. However, none of the guidelines have been finalized because they'll be finalized through CCME. PFAS, as Rita mentioned, is close to being published, I hope. And in the final column, you see the TRVs that we've used. And something you'll notice that several of the TRVs are written based on PFAS or based on PFOA, and that's because we don't have enough toxicological data to be confident in setting TRVs for all the PFAS. We have a lot more than there are available for the ecological receptors, but we only had enough data that to set TRVs for PFAS, PFOA, PFBA and PFBS, and PFNA at this point. So for the other substances, we've used a surrogate approach where we've taken either the TRV for PFAS or PFOA because we have the most confidence in those values. They're the most data heavy substances out there in the PFAS at this time. And we assume that these would be appropriate because the longer chain PFAS are considered more toxic in general than the shorter chain PFAS, and most of these guidelines are for the shorter chain PFAS. And we do have a TRV for PFNA, which is longer than the PFOA and PFAS. And as well, we assume that the fluorotelomers will degrade to their corresponding carboxylic acid, and therefore they would also be covered off by the PFOA TRV. We do update these very, I wouldn't say frequently, but much more frequently than any other guidelines that we develop. So every couple of years or every few months, we may have a change to one of these guidelines. So it's always best to check with us to make sure that you're using the right guideline if you are using these. Next slide, Rita. There are a couple of things for human health around these guidelines that are a bit peculiar. We don't see this in other guidelines that we've developed. Excuse me, for other substances. The first is additivity. As I didn't really have time to mention, but PFAS and PFOA are based on liver toxicity, and they've been shown to have very similar effects, toxic effects. So therefore, and as well, we've been looking at them from a firefighting aspect for the most part, where they're present in these mixtures, these AFFF mixtures, and the mixtures have changed over the years. So you often end up with PFAS and PFOA at the same site found together. So we do recommend that you consider PFAS and PFOA together when doing risk assessments at these types of sites. Some of the other substances do appear to have similar toxic effects, but we don't have as much confidence in the TRVs at this point, so we haven't recommended considering them additive, but that is something that you may want to consider if you want to justify that, and we would consider having additional ones being considered additive at a site. We're currently at Health Canada involved in some research around mixtures, quite a few mixtures, as well as some mixtures that we've come up with, as well as actual AFFF samples, to try and have a better handle on the TRVs, make sure that they're justified, maybe come up with more TRVs, and also support the additivity approach that we've been using. If we look at accumulation of PFAS in fish, we have seen several studies that have found high concentrations of PFAS in some fish, even in water bodies where they meet the surface water quality guidelines that Rita presented. So even if the fish are okay, we don't know if they would be safe for human consumption. We don't have any guidelines for human consumption of fish. And we know that that pathway can be operative at some sites. So if you do have a site that has an operative or that may have fish consumption, we do recommend that you evaluate that on a site-specific basis. There are some jurisdictions that have come up with guidelines for fish consumption by humans. Those could be considered. I've put a few here on the slide. I'm not sure if there are others. I haven't updated this slide in a couple of months, so there may be others out there, but that's something you should consider. Next slide, Rita. I don't think I'm going to say much to this slide. This just gives you an overview because time is, I see that our time is up, so I'm trying to speed through this. You can just see that by these dates that we really do update these guidelines quite regularly. Since 2010, when we first started evaluating the toxicity, we've already had, what, six updates to the values. So you should always check to make sure that you're working with the most recent values. And over here, in kind of a picture format, you can see that we have a lot more human health values than we do ecological at this point in time due to data insufficiencies. Next slide. Again, very quickly, to go over some of the other guidance documents that we've developed at the federal departments. There's a document entitled the Interim Advice for the Management of PFAS Contaminated Sites, which was updated in 2018 to include other PFAS. That's a document that provides some information on fate and transport specific to PFAS. It gives some background on the interim guidelines for human and ecological receptors that Rita and I just presented, as well as some information on remediation approaches. Then we have environmental site investigation guidance that was interim, has not been published, as well as a framework for human health risk assessment at PFAS contaminated sites. So for the interim guidance, unfortunately, due to how fast the science is moving on these substances, it was somewhat out of date by the time it was published. It does have some good background information that is still useful. Next slide, Rita. However, the interim advice, the interim and site investigation guidance developed by Transport Canada and the Human Health Risk Assessment framework that was developed by Health Canada provide a bit more detail on our detailed instruction on how to actually assess PFAS contaminated sites. They both address similar topics for the most part, such as identifying where the contamination would be, considering the type of how it was applied, the timing, the seasons, the effects of previous remediation activities, since people weren't really aware of PFAS up until somewhat recently. There's been a lot of remediation at some of these sites, and that could have had huge implications on where you're going to find PFAS at the site now. We provide information on sampling, and also how to select guidelines and criteria for conducting risk assessment on the sites. In addition to that, the Health Canada framework, which is a bit more recent, also talks about the precursors and degradation products associated with PFAS, the additivity of the PFAS and PFOA, the potential for accumulation in fish and country food that humans could be eating, as well as additional guidance for offsite contamination, because being at federal sites, we may have to be dealing with contamination that is going offsite and into land that is regulated by other jurisdictions. And next slide, this will be my last one, just quickly. The federal government has been carrying out quite a bit of research over the last, well, over almost 10 years now into remediation technologies, mostly at transport and national defense sites where most of the PFAS was identified in the federal family. Been focusing on tried and true to the extent possible, technologies that had already shown to be performant. Weren't looking at novel approaches because they really wanted something that would be applicable. For groundwater, they were mainly looking at absorbents and different treatment train options, so different designs of the treatment trains. So they've identified some absorbents that perform better, as well as the treatment train designs that performed better. As well as some of the limitations to these technologies, or some things that would have to be watched out for as if they're being used. On the soil side, they've been looking at stabilization technologies and destructive technologies. Most of that is still at the bench scale, but they have identified technologies that are both economically and technologically the most feasible at this point in time. I'm not going to give the details of that now just because of time. Some of the issues that they're running into are on the analytical side, the delays that can slow everything down. The impact of batch monitoring if you get breakthrough and how that can affect a whole batch of sample or water. What to do with the spent media that they're using for the absorption. Right now, there are no regulatory restrictions on PFAS landfilling, although there are some landfill sites that will not accept them, but officially there are no restrictions at this point. They're not necessarily designed to treat PFAS. If they do have a leachate treatment system, it may not be adequate, and some may not even have a leachate treatment system. So departments are looking at what to do with that spent media and considering that complete destruction of PFAS impacted media may be the only option at this point. So Rita, I'll pass it off to you so you can try and catch up on time. Sorry about that.
Okay, so I will try and catch up. We only have a few slides left here. Like I said before, we did establish an interdepartmental working group, and that's been in place since 2012, which is a great forum for sharing ideas and lessons learned. The workshop that we hosted, one of the more interesting things has been the desire to replace these fluorine-based foams with fluorine-free alternatives. There's a collaborative group with external stakeholders to define new foam standards with Environment Canada regulators, the foam users like D&D and airport operators, foam manufacturers, and both the Canadian and US Underwriter Laboratories Association. So they're trying to define new performance standards to use fluorine-free foams. And Transport Canada has also amended the Canadian aviation regulations to allow fluorine-free foams to be used. Before that, that wasn't even an option, but now since 2019, they are allowed to use these foams. And in fact, some airports have already started to adopt it. The Toronto Billy Bishop Airport has gone to fluorine-free foams. So it is starting to take off. Another aspect of collaboration is with respect to research. Health Canada is carrying out a number of research projects looking at PFAS and mixtures of PFASs and their precursors to better understand their toxicity. And that data is going to be used to support additional guideline development. And many of the remedial technologies and pilot studies that are ongoing that Darcy just mentioned involve academia, government, and private industry all working together to see what options are good. And also, we're not alone. The whole rest of the world is dealing with this. And we've got some really good international colleagues, particularly those in Australia. They seem to be very far out ahead on what they're doing. And rather than reinvent the wheel, we've been working with them to see what they're doing and maybe piggyback on some of their successes. So we keep in touch with them and see what's going on there. So I guess just a few closing thoughts. We still do face quite a few challenges with respect to PFAS and the sites that we're managing. With the sheer number of PFAS compounds and their precursors that are out there, we struggle to meet the needs for the toxicity data required to develop guidelines, and also the fate and transport data that's going to drive regulations and cleanup. Remediation technologies that are feasible, practical, and cost-effective are not quite there yet in terms of the Canadian environment. And also, we're not sure, maybe there's additional challenges posed by our northern climates that some of these technologies may be a bit not as effective. Some of the PFAS mobility, the budget constraints, delays, and other issues make PFAS sites very complex and potentially very big and very expensive. And while FICSAP does have funding, it is a limited budget, and they also are addressing other sites besides PFAS sites. So there's just, we just have to watch our budgets in that respect. Also, PFAS may migrate off-site, which causes challenges related to liability, due diligence, coordination with other jurisdictions, such as our provincial colleagues. And communication and sharing new PFAS information sometimes isn't timely and efficient. It takes a very long time to develop any new guideline, to get approvals. Publishing, sometimes translation constraints affect how efficiently guidance and guidelines can be distributed. So in terms of next steps, we to date have been focusing on the assessment and delineation of AFFF sites, our fire training areas. However, we do recognize that there are other sources on our federal sites, such as our landfills. So maybe we'll start to look at those. And people like Sean, when they generate some of that data, will certainly be able to help us pinpoint some of our problems there. We want to keep up with the latest science to develop new and updated guidance, and also prevention, such as I mentioned about the fluorine-free foams. However, at the same time, ensuring that any of these replacement products don't cause us any future problems going forward and creating other contaminated sites. So with that, I want to acknowledge my our colleagues that helped us put this presentation together. And if there are any questions. Joe, I'm not sure how you want to handle questions, or maybe there's not time.
We have I think we'll make time for a couple, and then we'll just eat into our lunch break later so that everyone gets their full presentation time. Thank you, Rita and Darcy, for a great overview and a great start to the day. If we'll take time if there are a couple questions, otherwise we'll move right into the next talk.
It's Terry here. If I could ask just one quick question, something that that I noticed when they produced the drinking water guidance, and I guess this question is for Darcy. But the slide that presented the health quality guidelines and the drinking water standards for PFAS. I'm curious, the C9, the perfluorononoic acid, or perfluorononanoate. The standards all seem to be an order of magnitude lower than the rest. Any comment on what's driving that?
I would have to go and look at the TRV for that. Again, I'm sorry, I don't keep I don't manage to keep any of this information in my head very long once I turn the page. But I'm sure, I don't think it's a question of uncertainty factors. I think it is the toxicity, but I'll have to look at it and get back to you. I can give you shoot you an email later.
Fair enough, thank you.
Okay.
Thank you again, Rita and Darcy. I really appreciate that.
Okay.
Our next presenter, Lindsay Patterson, a soil scientist with SLR Consulting. She's going to speak. We almost have a guideline for PFOS. What's next? Lindsay, over to you.
Great. Can you hear me there, Joe?
Yeah, looks good.
Great.
And sounds good.
Okay, well, a big thank you to the Environmental Services Association of Alberta and Joe for organizing this Emerging Contaminants Forum today. To begin, I would like to express my appreciation of being able to present this material from the ancestral and unceded territory of the Syilx people. The focus of my presentation is on per and polyfluorinated alkyl substances, emerging contaminants which are of particular importance to Indigenous communities given the potential for impacts lasting many generations. So I'm having trouble skipping to the next slide. So there we go. As mentioned in our opening keynote, the term PFAS encompasses a very large group of chemicals. In Canada, the majority of focus has been on a particular subset of PFAS called the perfluoroalkyl acids, which are fully fluorinated aliphatic substances. And these acids can be subdivided based on the N group associated with the chemical, whether a carboxylic acid or a sulfonic one. And the acids are also subdivided into those considered long chain substances where there's several carbons in the chain, and those that are considered short chain chemicals. The term PFAS also includes polyfluoroalkyl or partially fluorinated substances called precursors. These chemicals have the potential to degrade to more well-known perfluoroalkyl acids over time, and the perfluoroalkyl acids themselves do not degrade further under ambient environmental conditions. And when we say PFAS encompasses a large family of chemicals, we're talking about thousands of individual substances. The recent PFAS guidance issued by the Interstate Technology and Regulatory Council suggests that more than 4,700 PFAS could have been or may be on the global market. Darcy, who was just speaking, and her colleagues at Health Canada published an article this year in the journal Environmental Technology and Innovation, which identified that a smaller number of PFAS may have actually been in use in Canada, but still in the order of a few hundred chemicals. Regardless, we know that health and tox studies are only available for a handful of PFAS, and that commercial lab methods typically only identify about 30 individual chemicals. Heather Lord from Bureau Veritas Laboratories will be speaking later today on some advances in lab methods which can help us assess those substances that are not picked up with our more routine lab methods. And despite the potential for there to be hundreds of individual PFAS in use, or which have been historically used in Canada, as Darcy and Rita mentioned, CCME guidelines have only been derived to the near finalization stage for one chemical, the perfluorooctane sulfonate, or PFOS. And the guidelines for this particular PFAS have been a pretty long time in the making. I think, as they alluded to, guidance on PFOS at contaminated sites was developed for federal custodians in 2013. The 2015 Federal Contaminated Sites Action Plan PFOS guidance was mostly consistent with the values outlined in the draft CCME guidelines that were issued for public consultation. So it was a timeline of approximately 5 years from 2015 to now, hoping they're going to be issued soon, to take scientifically supported guidance for a single PFAS chemical to the guideline stage. It's enough to make a consultant cry. And in case you're wondering, yes, the disclaimer is legitimate. I can vouch for the safety of the photograph, as it's a picture of my own daughter. The parents in the audience today will understand why someone might take a picture of a crying baby, because as time goes by, your memories of eardrum shattering howls of an irritable infant will begin to fade. And it's only when you scroll through old photographs like these that you can say to yourself, how did we survive that? And if time allows, at the end of this presentation, I would love to share a video which my husband and I would like to refer to as Future Bridezilla, and we're keeping it for my daughter's wedding day. I should point out that as a nation, we're very close to issuing a guideline for a substance that was largely eliminated from production in North America approximately 20 years ago. This isn't to say that it's not vitally important to finalize the PFOS guideline. PFOS has been and continues to be a problem in Canada and globally. A study published in 2020 evaluating the fluorine mass balance in Northern Hemisphere marine mammals, such as polar bears and killer whales, demonstrated that PFOS continues to be the predominant PFAS detected in the livers of 11 different species. That being said, though, one wonders if we are adequately looking at the environmental data from our own backyard and planning ahead. The next PFAS reportedly on the books for CCME guideline development is the PFOA, or perfluorooctanoic acid. But the production of this particular PFAS was largely eliminated in North America by 2015. With the phase out of these and other longer chain perfluoroalkyl acids, chemical manufacturers didn't walk away from the production of per and polyfluorinated alkyl substances entirely. Rather, they pivoted their production to shorter chain PFAS and other fluorinated replacement chemistries. Substances such as Gen X, F35B, and Adana are frequently identified as emerging PFAS of concern, but data on environmental occurrence in Canada is limited, perhaps negligible, as was noted in a review from researchers at McGill and University of Montreal published last year. As you can tell, my daughter gave me a lot of material to work with. But rather than resorting to wailing when faced with the frustration of trying to determine what's next in the world of PFAS in Canada, the intent of my talk today is to take a deep breath and provide some thoughts on what PFAS should be the next focus of attention at a regulatory level from the perspective of somebody who has been evaluating PFAS at contaminated sites for 14 years. Over the next few slides, I'll draw upon data from various studies, including, in particular, Canadian data, to illustrate which substances I see as needing the most collective effort from academia, industry, and regulators. Spoiler alert, this slide actually covers some of the substances. I provide it here as a quick refresher for those who have trouble keeping their PFAS acronyms straight. Of note, perfluoropentanoic acid and perfluorohexanoic acid are 5 and 6 carbon perfluorocarboxylic acids, respectively, with the acronyms PFPEA and PFHXA. Perfluorohexane sulfonate is a 6 carbon perfluorosulfonic acid with the acronym PFHXS. And 6,2-fluorotelomere sulfonate is a polyfluorinated PFAS comprised of 6 fully fluorinated carbons and 2 carbons that are surrounded by hydrogen with the acronym 6,2-FTS. The most well-known PFAS sites in Canada are those related to the use or release of aqueous film-forming foams, or AFFF. And a study conducted on behalf of the U.S. Department of Defense at military fire crash testing sites has yielded some interesting results that perhaps give us some direction on where we need to focus our efforts at AFFF impacted sites. In the DoD-funded research, analysis of raw AFFF samples led to the identification of 57 novel classes of PFAS and a total of 240 individual PFAS associated with the foams. However, field data from the U.S. military AFFF sites suggests that although numerous PFAS precursors may be present in groundwater where AFFF was historically released many years ago, these substances have significantly lower concentrations than those of the perfluoroalkyl acids and fluorotelomere sulfonates that we routinely analyze among those 30 or so substances that commercial labs are currently quantifying. Based on various assessments the DoD researchers conducted of soils, sediments, groundwater, and raw AFFF, the researchers concluded that the precursor components of the foams had undergone some level of biodegradation upon release to the environment or were strongly sorbed to site soils and sediments. I should point out that the presence of PFAS precursors is more notable at sites where AFFF was released recently. Research conducted as part of the Lac-Mégantic disaster monitoring showed that routine lab analysis of perfluoroalkyl acids was missing a significant proportion of the overall PFAS in soil samples collected immediately following the disaster and the associated deployment of firefighting foams. However, subsequent sampling of AFFF impacted soils 2 years later showed that transformation of fluorotelomere precursors to perfluoroalkyl acids had occurred, with PFPEA and PFHXA in particular comprising more than 50% of the total PFAS in many of the samples. And this is something that SLR has also observed at sites with more recent AFFF releases, that transformation of fluorotelomere precursors present in AFFF concentrates to substances that we can actually detect with routine lab method happens relatively quickly once released to the environment. So we see it, within weeks and months. This is a slide from a Canadian AFFF site where release is reportedly seized in the mid-1990s. And what's notable is the mobility of substances such as PFPEA, PFHXA, and 6,2-FTS, particularly in comparison to PFOS. In this slide, PFOS makes a significant proportion of the PFAS in the source zone groundwater, but not in the down gradient groundwater. I should also note that results of total oxidizable precursor assays in the samples collected more than 450 meters from the source zone did not identify a significant pool of migrating precursors in the saturated zone. And this observation is consistent with my experience at some historical release sites located elsewhere in Canada, specifically that AFFF related precursors at historical release sites have shown some evidence of being spatially limited to identified source zones or release areas, suggesting, that there's some degree of retention of these compounds in site soils, while substances like PFPEA, PFHXA, and 6,2-FTS migrate further afield. This data is pulled from an article published this year. Earthworms were collected in situ from a fire equipment testing site at a major Canadian airport, and AFFF formulations currently used at the testing site were reported to be fluorotelomere-based, although the detection of PFOS, as noted in the left-hand column, suggests that PFOS-containing foam may have been used historically as well. Of particular note is the predominance of 6,2 and 8,2 FTS in the worm tissues. Concentrations of 6,2 fluorotelomere sulfonate ranged from 27 to 630 parts per million wet weight, with the researchers stating that the site maximum was actually likely the highest concentration reported to date in biota anywhere in the world. Go Canada. Yeah, maybe a dubious distinction. Beyond AFFF sites, PFAS has been used in fume suppressants for the metal plating industry, particularly the chrome plating industry, where they've been used for health and safety purposes to help minimize worker exposure to hexavalent chromium vapors. Data from source zone groundwater collected at one Canadian chrome plating facility is shown here. PFOS was the predominant chemical. However, PFPEA and PFHXA were present in significant quantities, and based on sorption and mobility differences, are expected to make up a greater percentage of the contamination as the plume migrates. PFBS, PFAS, which is regulated here in British Columbia, was also notably present in groundwater from this site. This is average concentration data for PFAS and Canadian landfill leachate. It's an older study, so I'm looking forward to the results of Sean's study. But this data showed that the differences of proportion of PFHXA, PFPEA in the landfill leachate, and that with the differences in physical chemical properties, those two particular substances would be expected to comprise a greater proportion of the overall PFAS as one moves away from the source. Similar findings were also noted in another study of Western Canadian landfill leachate, which also examined potential PFAS precursors. That study suggested that the perfluoroalkyl acids themselves comprise of between 50 and 95% of PFAS present in leachates. And of these, PFPEA and PFHXA appear to be the most notable, comprising 30 to 50% of the measured PFAS. This is data pulled from a recent study on the occurrence of PFAS in Canadian drinking water, and these represent 3 different tap water sources of the many investigated in Canada. So first, the researchers screened the drinking water samples for 133 different PFAS chemicals from different chemical classes. They then quantified concentrations of 17 perfluoroalkyl acids and 12 PFAS precursors considered to be target species. And although other PFAS were frequently detected in the water samples, further screening indicated lower concentrations than the specific PFAS noted here as being most prevalent in the samples. Although, thankfully for Canadians, the drinking water concentrations in this study overall were low, the data is indicative of the PFAS of importance in terms of their mobility through the environment to receptors. So what are the substances that I see as needing the most collective effort from academia, industry, and regulators based on the available occurrence data? Well, in addition to PFOS and PFOA, where the regulatory efforts are at a fairly mature stage, I would argue that it's PFPEA, PFHXA, PFHXS, and 6,2 FTS. In terms of guidance on acceptable levels of these substances in environmental matrices, we are really limited to the work done by Health Canada that Darcy spoke to earlier. She mentioned that Health Canada has developed drinking water screening values and have also developed soil screening values for these substances that are protective of direct contact with soil. Of particular note, the only other jurisdiction internationally that addresses 6,2 FTS in drinking water or soil is Denmark. For the substances in this table, actual chemical specific tox information was not sufficient to derive the screening values. As Darcy mentioned, toxicity information for surrogates of PFOS in the case of PFHXS and PFOA in the case of 3 of these other compounds were used to derive the screening values. And Health Canada's rationale is that the use of surrogates such as PFOS and PFOA are expected to offer a greater or equal level of protection than would be expected if chemical-specific toxicity information were available. Or reading between the lines, the use of PFOS and PFOA tox information is considered to be conservatively protective. Conservatively protecting human health is a good thing, but depending on just how conservative we are truly being, this can have huge implications for the management of these substances and by extension, the associated costs. It appears that Health Canada is actively working to address these types of uncertainties to support more effective site management, according to the Health Canada Journal article published this year, and as mentioned by Darcy earlier, Health Canada research includes projects to evaluate the toxicity of individual PFAS as well as 6 crude mixtures containing combinations of select PFAS to provide more confidence in the human health tox information used to derive the human health protective screening values. The area where progress is badly needed for these substances is in regard to criteria in support of ecological protection. To date, draft and finalized environmental quality guidelines that address the protection of ecoreceptors have been limited to PFOS. And as Rita mentioned, a federal environmental quality guideline is underway for PFOA. Unfortunately, as Rita did mention, it may be a while before we see federal environmental quality guidelines for short-chain perfluorocarboxylic and sulfonic acids. I do mention here on this bullet, I think an article that suggested that there may be some research projects underway. So maybe with time we'll see some environmental quality guidelines developed. But the fundamental problem here is that the basic research supporting the development of the eco-protective environmental criteria has been lacking. A search of the US EPA Health and Environmental Research online database illustrates the paucity of information for some of the PFAS, particularly PFPEA and 6,2-FTS, in comparison to the research that's been generated for PFOS and PFOA. To be honest, I suspect that the counts for PFOS and PFOA are on the low side, but I'm simply trying to provide a qualitative comparison of the amount of work that's been focused on those 2 chemicals and the relatively lesser amount of research that's been done on other substances that are showing significant occurrence and mobility through the environment. What is evident is that we presently have a limited information base from which to move forward. However, there are some indications that we should be seeing a substantial increase in information for some of the substances. For PFPEA and PFHXA, 1/4 to 1/3 of the total number of references in HERO were generated in 2019 and 2020 alone, with about 2/3 having been generated in the past 5 years. Sadly, though, research related to 6,2-FTS has simply plodded along at a fairly constant and low rate since around 2007. Gathering data on the ecotoxicity of various PFAS has been a major research thrust for the US Department of Defense through its Strategic Environmental Research and Development Program, or CERDIP. 2 reports were issued in 2020, with the data on this particular slide having been pulled from one of those reports. Site assessors should review the documents directly to confirm the applicability of the tox data to their situation. The point here is that despite significant efforts expended by contractors funded by the US Department of Defense, there are still enormous basic knowledge and basic research gaps when it comes to the PFAS of particular relevance at Canadian sites. Even the no observed effects levels and low observed effects levels, NOLs and LOLs, provided for PFHXA and PFHXS in the report are based on only 3 studies each in mice and rodents, and that's not a lot of research data. The second CERDIP eco-tox report released this year focused on the development of risk-based screening levels for eco-receptors. And as you might expect, based on the extremely limited eco-tox data noted on the previous slide, the development of risk-based screening levels for soil and groundwater has been greatly limited as a result. Now, bioaccumulation occurs when uptake of chemicals exceeds excretion or metabolism and results in an increase in internal tissue concentrations relative to the environment. And this process is known to vary widely among different individual PFAS. One of the CERDIP projects attempted to compile bioaccumulation metrics for many of the perfluoroalkyl acids, and key findings from the study are summarized here. Of particular note is the tendency for PFHXA and PFPEA to behave differently from the more well-studied long-chain perfluoroalkyl acids. And for those in the audience I lost once I brought up a chart referencing pelagic invertebrate bioconcentration factors, don't worry, it's just a minute or more so until we watch the Future Bridezilla video. Now, with the Americans making limited progress on these 4 substances, are other members of the international community doing any better in deriving environmental criteria? In Italy, a working group was set up to develop environmental quality standards for PFOA and related short-chain perfluoroalkyl acids in surface waters. Quality standards were developed for different environmental protection objectives. And while quality standards could be derived using sort of the gold standard of the species sensitivity distribution approach for PFOA, the limited data associated with the short chain perfluoroalkyl acids required a more deterministic approach and application of uncertainty factors. The data for PFHXA were insufficient to derive any kind of quality standard, and PFHXS and 6,2-FTS were not included as substances of focus in their study at all. The German states Water and Soil Consortia have compiled probable no effects concentrations for 3 of the 4 substances in surface water. An assessment factor method was applied since there was insufficient data to apply that species sensitivity distribution approach. And basically, this entailed selecting the lowest effect value and then applying a safety factor of between 10 and 100. And like elsewhere, 6,2-FTS was not a PFAS of focus at all. The Australians have taken an approach of focusing on PFOA, PFOS, and PFHXS as their primary indicators of other PFAS as part of their National Environmental Management Plan. And as part of that approach, they apply Canadian federal environmental quality guidelines for wildlife diet items to the sum of PFOS and PFHXS. As an aside, I do wonder whether solely focusing on these 3 particular PFAS is truly health protective. Canadian experience of PFAS migration at AFFF sites suggests that it may not be. So in summary, addressing knowledge gaps and regulatory needs for perfluoropentanoic acid, perfluorohexanoic acid, perfluorohexane sulfonate, and 6,2-fluorotelomere sulfonate cannot be easily solved by drawing upon the experience of other jurisdictions. Rather, I hope my talk today has emphasized the pressing need for collective efforts from academia, industry, and regulators in Canada to address PFAS, which are of prevalence in our own backyard. And hopefully some of you can be part of those efforts. Once again, I'd like to express my appreciation to ESAA for organizing this forum, and of course, to you, the audience, for attending. Thank you.
Thank you, Lindsay. I appreciate that. Looks like we have a couple questions. If you have questions, please type them in the question box and I'll get to a few of them. Lindsay, should analysis of PFAS compounds become more of a standard practice in site assessment and remediation activities, including landfill and wastewater monitoring?
Yeah, I would say so. I think that's what the data is suggesting, but Sean's study is going to provide some great insight into that.
Okay. Is incineration still being recommended as the best method for disposal for soil? Yeah.
Was that two parts to
Soil
that
and
question?
AFFF concentrate.
AFFF concentrate. Well, Environment Canada has, I think, provided a fact sheet. Maybe Rita can speak to that on what to do with AFFF. But in terms of soil, there's very little in the way that's a destructive technology. So are you looking at, what can we do to completely break those substances down? That carbon fluorine bond is so strong. And right now, its thermal technologies are the only ones that are showing for substances like PFOS, which often are the predominant PFAS in soil at many of these sites. It's requiring high temperatures to fully mineralize that.
Okay.
Lindsay,
Go ahead.
Sorry, it's Rita. We do have a fact sheet for and advising incineration for activated carbon, waste carbon, that kind of thing. We are taking a step back, but there's been some studies just out to suggest that some of the PFAS compounds are getting out the stack, and it's promoting some widespread distribution of some PFAS compounds. This was a study down in the States. So anyway, as it stands right now, that memo still stands, but I just wanted to let people know that we are taking it under advisement and maybe looking at that again. I don't know what else to do with it, but that's being considered.
For sure. And I mean, I've heard of in the US, AFFF is being solidified and then put in hazardous waste landfills.
Yeah, I think D&D is looking at something like that too, in a bench scale work. Yep.
Okay, great. No other questions for you, Lindsay. So thank you again, and thanks for your help with getting me straight on this and getting it set up. So appreciate that.
Oh, no worries, Joe. Much appreciated.
Okay. Our next presenter is Terry Obel with Bureau Veritas Labs. Let me just switch presenters here. Oops. 1 second. Terry is going to be speaking on 1,4-dioxane, a re-emerging contaminant. Terry, over to you. The presentation looks good.
Okay, so we've got the title.
Yep, and we got sound.
Great, and I'd echo what Lindsay has said. That I very much appreciate the opportunity to present today in ESAA's forum on emerging contaminants. Always glad to participate. I do want to thank Lindsay for sharing the photographs of her daughter. All I can say is, oh, I remember those days. So thank you for that. In an industry and a market that is dominated by the acronym PFAS, I thought, well, in deference to the English comedy troupe Monty Python's Flying Circus, and now for something completely different. I'm going to speak on the compound 1,4-dioxane, and I've titled the presentation a re-emerging contaminant. So what I'll talk about is what I've referred to as the 1,4-dioxane story. I'll speak a little bit to the chemistry of this compound, its history. It's sort of in the shadow of PFAS. Why do we care? I'll speak a little bit about the exposure and toxicity. Then I'll try to answer, why is it a re-emerging contaminant? Why is there this renewed interest in 1,4-dioxane? We, as a laboratory, we're getting more requests now to analyze for 1,4-dioxane in groundwater and at increasingly lower levels. Why is it special? Talk a little bit about the sampling and analysis of the compound, and then I'll speak to some of the treatment and remediation options. And then I'll speak to the future of 1,4-dioxane, some of the regulatory requirements or developing regulatory requirements, and some of the market considerations, which provides some food for thought. So when we talk about the chemistry of 1,4-dioxane, this is the molecular structure on the left. I'll keep the chemistry to a minimum, but it's basically 4 carbons and 2 oxygens and 8 hydrogens. It's generally presented as that sort of flat ring structure, but it exists in a number of what are called conformational isomers, and I've shown the chair configuration on this screen. I've provided some basic chemical data for your information. It's from a physical standpoint, it's a clear, colorless liquid. I understand it has a pleasant, sweet smell. I've never smelled 1,4-dioxane. But what I want to draw your attention to is the boiling point and the water solubility. And this is what leads to some of the challenges with the analysis of these compounds, and it also impacts some of the remedial options. From a behavioral standpoint, it is recalcitrant, it's persistent, but it's because of its water miscibility, it is highly mobile. What I do want to highlight is don't confuse 1,4-dioxane with dioxin. People have done that in the past. They're not the same thing. 2,3,7,8 tetrachlorodibenzo-P-dioxin, TCDD, often referred to as dioxin, is okay, the technical vernacular is super toxic, whereas 1,4-dioxane, it's still, the toxicity information is kind of like PFAS, it's elusive, but all indicators are that it is linked to carcinogenicity. But I do want to highlight for some out there that 1,4-dioxane is a different compound from dioxin. In terms of its history, and there's been a lot of work done by the Interstate Technology and Regulatory Council. And so I could have put together a nice timeline, but they did such a nice job that I lifted it from one of their documents, and I'll refer to that document later on. But 1,4-dioxane, I mean, it was first synthesized in the late 1800s, and then it really didn't grow legs from a production standpoint till the 1950s. And because of its utility as a stabilizer in halogenated solvents, when they interact with metals, they tend to they can degrade the solvent. So the 1,4-dioxane was added as a stabilizer. And what's interesting to note about this plot is that the production of 1,4-dioxane kind of tracked the same path as the use of some halogenated solvents. You've got 2 peaks here. The first peak represents its use as a stabilizer in trichloroethylene, TCE. And when TCE was looked at from an environmental and from a health standpoint, and the usage decreased, so too did the manufacturing of 1,4-dioxane. And then you'd have a second peak because the TCE was being replaced by 1,1,1-trichloroethane, so 1,1,1-TCA, and the 1,4-dioxane was added to that as a stabilizer. But we all know with halogenated solvents, TCA being one of them, that they've been identified as ozone depleting substances. There are certain health effects that the use of halogenated solvents has declined since then, and you're seeing the same thing with the manufacture of the 1,4-dichloroethane. And then, and this is germane to the discussion and perhaps material to the question of it being a emerging contaminant. 1,4-dioxane was added to the list of compounds monitored under the Unregulated Contaminant Monitoring Rule 3 in the US. and I'll speak to that a little bit later. So in terms of its usage, as I said, the primary industrial use has been the stabilization of halogenated solvents. And as I said, it declined in the 70s and 80s amid health and environmental concerns around trichloroethylene, but then it experienced a little bit of a resurgence as the use of TCA increased. And it was suggested that about 90% of the 1,4-dioxane, the volume of 1,4-dioxane manufactured was used as a stabilizer. And in the 70s and 80s, you're talking like 25 million pounds per year. So there's still like 2.5 million pounds being used for other manufacturing processes. And these are listed here. This is just, it's not a comprehensive list, but it just shows that 1,4-dioxane, while we know it as a stabilizer in halogenated solvents, and that was sort of the initial thrust for monitoring 1,4-dioxane, its reemergence as an emerging contaminant still is based on its use as a stabilizer in halogenated solvents, but also it was used directly or generated as a byproduct in the manufacture of, among others, plastics and polymers, inks and paints, adhesives, automotive fluids, and consumer. Imagine the word products after that, so consumer products. When we talk about the toxicity of 1,4-dioxane, there is still it's still iterative. There's an acute toxicity. So if you come into contact with high concentrations of 1,4-dioxane, it impacts the liver, the kidney, the central nervous system. The chronic toxicity, it's being associated with specific types of cancer. So IARC and the ATSDR have classified 1,4-dioxane as possibly carcinogenic to humans based on animal studies. So the animals, the lab rats, don't like it, and but they don't have sufficient information on human toxicity to define it as a human carcinogen. So it's possibly carcinogenic to humans. It's somewhat toxic to aquatic plants and invertebrates. In the United States, the U.S. Environmental Protection Agency classified 1,4-dioxane as likely to be carcinogenic to humans. And it's that reassessment that has kind of driven this reemergence or this renewed interest in 1,4-dioxane as a contaminant of concern. It's moderately persistent in the environment, but it doesn't bioaccumulate. And this is interesting because if you consider the chemistry that I presented earlier, it may exert a toxic effect, but it doesn't bioaccumulate like the organochlorine pesticides or PFAS bioaccumulates in the protein-rich organs. What are the sources of exposure? The primary source is ingestion. If you are ingesting or drinking contaminated drinking water, that's sort of the primary source. I do note here that the groundwater contamination, because of the mobility of 1,4-dioxane, the concentrations that you'll find in groundwater are typically higher than what you find in the surface water, because it'll migrate its way down to the lower aquifers. Contaminated food has been suggested as a source of exposure to 1,4-dioxane. Consumer products using or containing 1,4-dioxane, there's a plethora of them out there, and it's not necessarily that the 1,4-dioxane was used in the manufacture of the consumer products. As I said before, it can be a byproduct of certain chemical processes used in the manufacture of things like shampoos, cosmetics, etc., where if you have polyethylene glycol or ethylene glycols, it can form 1,4-dioxane in the manufacturing process. And then there's occupational exposure. 1,4-dioxane having been used in manufacturing processes. It's used in certain laboratories. So basically, industries using 1,4-dioxane or products containing 1,4-dioxane represent a source of occupational exposure to this compound. So why have I referred to it as a emerging contaminant? We've been analyzing 1,4-dioxane for many years, and so when you look back to 2002 and even before 2002, 1,4-dioxane referred to as a little-known compound. But what you were finding is it was showing up in groundwater wells that were contaminated with halogenated solvents, and then that's where people started getting interested in it. So this is an area in Ontario, and you can see there is a plume of halogenated solvents. This is actual work that was done. These are wells that supply a water treatment plant, and it's been work that has been ongoing for some time, and it is public domain. But you can see that that there is a dioxane 1,4-dioxane plume that is impacting the wells, in addition to the TCA. What's interesting to note is the presence of a historic and old dump site, an old landfill. And looking at this diagram, for those who look at hydrogeology, I bet you can't guess which way the groundwater is flowing. But you can see that that the 1,4-dioxane does have an impact here. What's interesting, and this is just as an aside, is you would think that the mobility of 1,4-dioxane would suggest that the plume travels much further than the plume for the halogenated solvents, and that in fact is not always the case. That and there have been a number of theories on why that sort of behavior. But just to show you that back in the day, there was a lot of interest in monitoring 1,4-dioxane in groundwater systems, particularly those that were supplying municipal drinking water. The historic environmental interest, as I said, was primarily its use as a chemical stabilizer in halogenated solvents. So just I grabbed a photograph of something that said trichloroethylene, but really the primary and the greater use was 1,1,1-trichloroethane, but also tetrachloroethylene or perchloroethylene, PCE. As I said, it was added to the list of compounds monitored under the unregulated contaminant monitoring rule in the United States between 2013 and 2015. And again, just as an aside, this industry dominated by PFAS, so are about a half a dozen PFAS were part of the UCMR3. But they were testing for 1,4-dioxane at concentrations above a detection limit, so above 70 parts per trillion or 0.07 parts per billion in groundwater. They tested about 4,500 to 5,000 public water systems and collected data. So the number of groundwater samples was about 41,000, surface water 28,000. And interestingly, and I don't have the diagram, 1,4-dioxane was the organic contaminant. There were metals analyzed as well, but it was the organic contaminant that had the highest number of detections in these groundwater wells or in these groundwater samples. And it was the organic that had the highest frequency of detections above the reference value of 0.07. So now, and you can see sort of the distribution of contamination across the United States for 1,4-dioxane. So you can start to see how people are looking at this going, this is something that, that we may want to start having another look at. So historically, the focus has been on looking for 1,4-dioxane in at sites that have been impacted or where you've had a release of halogenated solvents. But now it's you look at it. Remember, I said polyethylene glycol or diethylene glycol. It can be a byproduct in the manufacture. Antifreezes are potential sources of no, here you go. I wanted to say PFAS. 1,4-dioxane. Airline de-icing fluids, same thing. It is the manufacturer of it. Personal care, personal care products. And I hope I made it blurry enough so that you can't really see any names. Don't want any lawsuits. This one, detergents. In the manufacture of detergents, 1,4-dioxane has been used or is a byproduct. As I said, inks, paints, coatings contain 1,4-dioxane, but as I said before, the suggestion that one of the exposure pathways of 1,4-dioxane in humans is food. Food packaging materials have been shown can be a potential source of 1,4-dioxane. So, back to the question, why is it a emerging contaminant? It's going beyond the halogenated solvents, and people are starting to develop an interest in it, and not unlike PFAS. It was the same thing many years ago when there was that initial interest or that initial thrust looking at PFAS as a contaminant of environmental concern. So where are you going to find, what are the major sources of 1,4-dioxane impact? Industry, the improper disposal of chlorinated solvents that may include 1,4-dioxane as a stabilizing agent. Landfills are getting a lot of attention these days, and so it's the same thing here. We've been involved in a number of projects where 1,4-dioxane has been a significant contaminant of concern in landfill leachate and the impact on the groundwater system. Wastewater treatment plants. I'll speak to the treatability and the remedial options for 1,4-dioxane, but they haven't been treating for it, so they are a potential source of 1,4-dioxane impacting the environment. Military sites, there's a huge interest by the military in 1,4-dioxane and getting as low as possible detectabilities on groundwater, because it goes back to that initial interest, basically halogenated solvent plumes. And airports, runoff from airports. See how it's kind of paralleling PFAS, but the de-icing fluids that are used in airports, they run off the planes and run off the property kind of thing and impact the environment. So when it comes to sampling for these compounds, they're not as extraordinary as PFAS. 1,4-dioxane can be analyzed, and I'll speak to the different types of analyses shortly. It can be analyzed as a volatile organic compound, or it can be analyzed as a semi-volatile organic compound. This just describes some of the containers. Yes, Teflon lined lids, back to the Teflon lined lids, are apropos. But it's basically treated as a volatile or a semi-volatile compound, where these are general preservatives and hold times. Where you'll see differences is if you start looking at 1,4-dioxane at trace levels, where if you're treating it as a volatile, for instance, in water, the preservation is not, but rather sodium bisulfate vis-a-vis the EPA protocol for low-level volatile analyses. It's the same thing with soil. Rather than using methanol, the soil is introduced into the 40 ml VOA vial in a sodium bisulfite solution. when it comes to analyzing the 1,4-dioxane as a semi-volatile compound, it's essentially cool to 0 to 6 degrees, unless it's a chlorinated water source where you want to address the chlorinated water with, you want to quench the effects of the chlorine with sodium thiosulfate. And there have been suggestions to use sodium bisulfate if you are analyzing at ultratrace levels. But just like any field sampling program, proper QA needs to be in place. Equipment decontamination is something that you do need to focus on, and is ensure that there is no residual detergent on your sampling apparatus. Remember that the detergent manufacturing can introduce 1,4-dioxane into the cleaning products. Just a suggestion or recommendation, be sure to collect equipment blanks when collecting samples for 1,4-dioxane. I always bring up this guy. I've used this photograph before about this guy that is the GQ sampler, and everybody knows how unrealistic that sample that photograph is of field sampling activities. So I found another one. I'm going, now we're talking. This is field sampling where you've got snow and rain blowing in your ear sideways and you're trying to collect a sample. I just thought I'd share that with you. From an analytical standpoint, as I said, it has been checked, treated as a volatile, in which case the analysis would be by purge and trap gas chromatography with mass spectrometry. The problem is with an ambient purge and trap, and this has been demonstrated by Bill DiGiuseppe and Thomas Moore in the United States, that the variability, the precision and the accuracy of an ambient purge and trap is lacking, and so by extension, the limits of detection and the reporting limits are going to be lacking. If it's being analyzed
Terry, it sounds like we're having problems with your audio.
as a volatile, it is strongly encouraged that it improves the precision and the accuracy and the reporting limit. I think the direction that the industry is going in from a laboratory standpoint is to treat it as a semi-volatile, using either liquid-liquid or liquid-solid extraction, or the USB method 522, the drinking water method. What we're finding is far superior, using solid phase extraction with gas chromatography, with tandem mass spectrometry. If you don't have a GC triple quad, just doing it with a single quadruple mass spectrometer. So from Bureau Veritas' standpoint, like all analyses, you eliminate all sorts of contamination. Like PFAS, isotope dilution using the isotopically labeled analog of the compound of interest is preferred. So in this case, it's 1,4-dioxane, where the hydrogens are replaced with deuterium. Solid phase extraction coupled with gas chromatography mass spectrometry, or gas chromatography with tandem mass spectrometry, and the reporting limits are at the part per billion and sub-part per billion levels for water, and soil, it's the sub-part per million and approaching the part per billion level for 1,4-dioxane. Just being mindful of the time. When it comes to remediating 1,4-dioxane, and I alluded to this at the beginning of the presentation, you have to consider its physical and chemical behavior. So I've labeled this as a problem statement. It's miscible in water. It is chemically stable, doesn't hydrolyze under typical conditions. It's got a low octanol water partition coefficient, so it doesn't really absorb or adsorb to organic carbon. And it's got low Henry's law constant, so it's got low volatility. It doesn't mean it has no volatility. Like I say, it's analyzed as a volatile, but that can be problematic at times because of the low volatility. So when it comes to remediating for 1,4-dioxane, these are there are other remedial options, but I've just presented the ones that are referred to as being fully demonstrated. And you can do they're ex situ options, so pump and treat, where you're using different types of oxidation. There are electrochemical approaches to remediating 1,4-dioxane. Aerobic biodegradation, it degrades under aerobic conditions, so if you're using a bioreactor. And then there are sorptive resins. Like I said before, it doesn't absorb to organic carbon, but things like Ambrosorb can be used to treat 1,4-dioxane in water samples. Then there are in situ options. There's monitored natural attenuation using, relying on the physical, chemical, and biological processes that occur in situ. Phytoremediation has been demonstrated as an option for in situ remediation of 1,4-dioxane, but then chemical oxidation using persulfate or a modified Fenton's reagent. All of these bring 1,4-dioxane at various concentrations in the contaminated matrix to less than 1 microgram per liter. From a regulatory standpoint, there aren't a whole lot of regulations in Canada, but certainly Health Canada published a discussion document back in 2018, and they are proposing a drinking water standard of 50 micrograms per liter. British Columbia has included it in the contaminated site regs, the amended contaminated site regulations from 2017 at 1.5 micrograms per liter in drinking water. Ontario doesn't have a drinking water standard per se under Regula 169, but the site remediation, the regulation 15304, they've identified a soil target of 0.2 micrograms per gram and a groundwater target of 50. What I've done there are different uses of the soil and the groundwater. So the property, I've just taken the lowest regulatory standard. US EPA has issued a health advisory of 35 micrograms per liter, but they have recommended a regional screening level of 460 parts per trillion, so 0.46 micrograms per liter. A number of states, actually a lot of states across the US are now setting either guidance values or regulatory standards for groundwater and drinking water, and they range from below the regional screening level that the US EPA has put forward to upwards of 200 micrograms per liter. So I was just like my question about the perfluorononoic acid in why is the standard an order of magnitude lower? I question what is it about the different states that some are recommending that the risk-based value or the health-based value is subpart per billion, and others are saying it's upwards of 200 parts per billion. But it is what it is, and I think it's growing. So again, supporting the notion that 1,4-dioxane is a re-emerging contaminant. World Health Organization has adopted the 50 microgram per liter threshold for groundwaters and drinking waters, and Japan as well. So when it comes to future market considerations, and this is something that that we looked at it at Bureau Veritas, and I find it interesting that the demand for remediation by the type of contaminant, and this is taken from a 2019 publication of the Environmental Business Journal looking at remediation markets, is the strongest are the predicted or projected demand is strongest with emerging contaminants, PFAS, other emerging contaminants, and there it is, 1,4-dioxane. That the focus on these compounds is only going to increase as compared to what we have all known to come in and love as the contaminants of concern on a lot of contaminated sites, hydrocarbons, metals, volatiles, PCBs, etc. So this is again suggesting that there is a renewed interest in 1,4-dioxane, or maybe it's the same interest only on steroids for 1,4-dioxane. So to summarize sources of environmental impact by 1,4-dioxane is primarily halogenated solvent release. But what is driving this renewed interest in 1,4-dioxane in groundwater systems, you have sites that they're finding 1,4-dioxane, but no halogenated solvents. So is that, there's increased evidence of other sources of contamination, example, landfills, or, other materials that are contributing to 1,4-dioxane. The analytical methods, best practice is favoring isotope dilution, gas chromatography with tandem mass spectrometry, or gas chromatography with a single quadrupole mass spectrometer, but using a technique called selective ion monitoring to allow part per trillion detectabilities in water. The values that I presented from Bureau Veritas, that's based on a single quadrupole. We are validating our GC triple quad for 1,4-dioxane, and the initial results are showing that yes, it is going to provide a substantial decrease in the reporting limit. An increasing number of jurisdictions are developing health-based and provisional guidance values, and in some instances, regulatory standards for 1,4-dioxane in groundwater and drinking water. And really, to answer that question, is 1,4-dioxane a emerging contaminant? It's sure looking that way. So I just want to present to you, there's a plethora of resources out there. These are some key resources that if you're interested, I encourage you to look into. There was a publication in 2010, as I mentioned the name before, Thomas Moore put out looking at 1,4-dioxane and other solvent stabilizers. Bill DiGiuseppe contributed to it from Jacobs. As I said, there's real interest on the part of the Interstate Technology and Regulatory Council, the ITRC. They have established a team that is looking at 1,4-dioxane. They have published a number of valuable fact sheets similar to the ITRC team that was working on PFAS. The EPA, this is just their technical fact sheet from 2017, but they have a lot of updated information. So if you're interested, I encourage you to hop on the EPA website to look into 1,4-dioxane. And as I said, Health Canada is also focusing some attention on 1,4-dioxane. So I feel, yeah, it is genuinely a emerging contaminant. Here's my contact information. If you want more information, or if you have questions that you want to chat about, feel free to contact me at these coordinates. And with that, I'll end my presentation. Hopefully, didn't go too long.
Thanks, Terry. Great presentation as always. Really appreciate that. I got a question for you. How do results compare between VOCs and SVOC methods? Which method would you recommend for the 1,4-dioxane assessment?
The VOCs, if you're using an ambient purge and trap, they're not even close. Okay, there's very high variability there. If you're not using isotope dilution, you don't even have a running chance of comparing. Like I said, the best practice is focusing on semi-volatile analysis using isotope dilution. Having said that, and this is one that Bill DiGiuseppe and I have talked about, he advocates the heated purge and trap, and the heating is an absolute necessity because it tends to dissociate the 1,4-dioxane that may be through physical processes stuck to the water. The ruling thought is to treat it as a semi-volatile organic. So in other words, liquid extraction, or I would advocate the solid phase extraction because you have the ability to concentrate samples, a higher volume of sample through the solid phase media. But we do have a lab that has used the heated purge and trap. And if you're just doing liquid extraction with isotope dilution and GCMS and comparing it to a heated purge and trap analysis with isotope dilution and GCMS, they're comparable. But I find that the data variability is minimized with treating it as a semi-volatile.
Okay, thanks for that, Terry. If anyone else has any questions for Terry, please reach out to him. We're going to take a short break right now. Let's reconvene at 10:35. I know we're running late, but we'll make up the time at lunch so the upcoming presenters have a full time to speak. No need to log off, just stay on, and we'll just come back in about at 10:35. So thank you. Enjoy your coffee. Hey Terry, you can turn off. If you turn off your mic, that'd be great. Thanks. Hi Brian, are you online? Brian Shaw? Brian, are you online?
Yes, I am.
Hey, good. I'm going to switch presentation. I'm going to switch view to you so you have control so you can set up your presentation.
Okay.
Should be a message on your screen that says make you the presenter.
Okay.
Okay, there's a, at the top of the screen there says display settings.
Show on screen.
No,
Which are you seeing? One of my screens?
yeah, the PowerPoint screen.
Yes.
Says slides 1 of 20. There's a box there at the top that says display settings.
Oh, yes.
Switch that to swap presenter view. Perfect.
Not your first rodeo, Joe.
No, no, no. So we'll get started right away. You still have the same amount of time.
Okay. Just start at 9:35.
Yeah, I'll introduce you. Yep.
Okay.
Welcome back, everyone. Hope you had a chance to grab a coffee, take a quick break. We'll move right into our next presentation. We have Brian Shaw, a senior technical support scientist with Caro Analytics, testing for SARS-CoV-2 in wastewater. Brian, go ahead.
Okay. Thank you, Joe, and thanks for everyone in the audience today for joining. So, as Joe alluded to, this talk is going to be on what would be considered a very new emerging contaminant. I thought it'd be interesting just to kind of go through some of the current dialogue and research on COVID testing in wastewater. So this has garnered some attention for the purpose that the idea is if you can track the presence of the COVID virus in wastewater, you can potentially get an idea of where cases are going up. Is there a way to correlate the virus in the wastewater to the number of cases in a population? Is there a way to isolate where cases are present without mass testing? And so essentially the reality of it is that we will shed that virus if we've been infected with COVID-19. And so wastewater-based surveillance is not a new technique, and I'll get into that shortly, but anything related to COVID right now, it's a very unique time when it comes to publication of data. Everything's widely available. You don't have, nothing's behind a paywall. Everyone's sharing information so that we can get things done as fast as possible. So it's an interesting time. And so this presentation is really going to go through kind of the current state of the research, give some information about what testing is like, how you would test, and some of the challenges that need to be worked out. And so I'll go through all those in my next few slides. So you will notice I've everything's referenced. So if you're interested in anywhere these references came from, they're all on the bottom of the slide. So as I said, there's quite a number of publications and a number of groups involved. But the first that I kind of came across this idea was at the beginning of April. There was an article posted in Nature just discussing some of the work that was coming at that time, primarily out of the Netherlands, but also the US and Sweden. And so what they had done in the Netherlands anyways, was they had detected the virus at an airport 4 days after the first case was clinically reported in the Netherlands. And so they had archived samples, et cetera, and they were able to go back and see that they were detecting the virus through a pretty rudimentary technique at the time, which has been slowly developed since then. Now, what we call this wastewater-based epidemiology, and epidemiology is a word that we've heard a lot in the last 6 to 9 months. which literally means the study of what is upon the people. So I just want to quickly introduce this topic because it's continually referenced throughout. And when we look at the history of epidemiology, there's one person, John Snow, who was widely regarded as the first epidemiologist through addressing a cholera outbreak in London in 1854. And you know, when I read this, I realized I'd heard this story, and you may have heard it yourself, and didn't realize that this was actually the birth of epidemiology. But this was a situation where part of town was all using the same water tap, and obviously there were, at the time, you know, there's no chlorine, there's no disinfectant, and so he was able to map out where these infections were taking place and trace it all back to this one water tap, which obviously was then replaced and addressed. And so it's essentially going to the root of the problem and following that, tracing that track to get back to where this is all starting. And this is a technique that's used for various purposes, such as, you know, measuring the success of vaccination, eradication of disease. Polio is one example where they've used wastewater to track whether that virus is still present. There's examples, simple examples, even in Canada. Stats Canada in 2019 released some data that they had done on related to narcotics use in major cities across Canada. And so this graph on the bottom right here is just kind of showing some concentrations per capita in grams of THC, in this case, that they found in the wastewater in each city. So the first thing most people ask, and you know, this, like I said, this has been in the news. A lot of people have probably heard about this idea. And the first thing that people wonder is, how do I test it? And so that's one thing that's being addressed right now. There's a lot of researchers working on this. There's working groups in Canada, the US, many countries who are all sort of combining resources to try to address this. And so just a quick overview. You take a standard 24-hour composite wastewater sample. So the good news is, especially for anyone who's doing the sampling, it's nothing new. It's a sample you've already taken before. And the main focus right now is the concentration technique. So as you can imagine, with the flow rates on some water treatment plants and the level of virus you would expect, some sort of concentration is going to be required. And I've just highlighted here 4 different techniques that are being used. They all vary, you know, using a centrifuge, maybe some additives, some sort of filtration, where you can take a high volume of water and extract as much RNA of that virus as you can. And ultimately, detection via qPCR. At this point, PCR has become a household word. And so I thought I'd quickly just introduce that technology. I know we've probably a lot of us have heard of the PCR test for COVID testing for clinical diagnosis. And so what does that actually mean? So PCR is a technology that's been, you know, around for 30 plus years, and it's quite fascinating what it's able to do. And so the idea is that, similar to how our DNA, for example, is replicating in our cells, PCR takes advantage of that, and you add a primer which essentially amplifies the DNA or RNA in the case of COVID. And so as you can see here, as you pass through each cycle, you're amplifying that original sample and producing more and more of the RNA or DNA, which allows you to then detect it even from a very small level, because you've created various copies of the RNA chain. And this is kind of for interest's sake, you know, just to get into a little bit more detail, and then I'll move on from the PCR. But you know, I thought it was interesting just to kind of show the virus and how the PCR technique is being used to identify its presence. And so you see here we have spike, nucleocapsid, membrane envelope. These are all different proteins that are being looked at by the genetic target of the primer. So in this case, the kit that you add to the sample is amplifying the RNA that essentially creates these unique species or structures on the RNA or on the COVID virus. And so that's how it kind of works, is you identify some unique pieces of this virus, and then you focus on those for your PCR test. And so this is just a graphic that shows the various proteins that are being focused on. Now, so how is it tested? I want to mention the Canadian Wastewater, or the Canadian Water Network, I should say, who has set up a wastewater coalition. And they're doing pilot studies, interlaboratory studies on different methodologies, comparing results on the same sample to see what kind of recoveries people are getting, and trying to narrow down what the best practices are for measuring this virus. I mean, there is certainly people who are testing for it, reporting results, and you can do that. You can definitely you can find the virus in the wastewater. It's just a matter of, what does that mean? Do we know that we found it? Did we find all of it? Those types of questions. And so there's 8 design principles that they're focusing on. And the 3 that that are worth highlighting for the purpose of this presentation is achieving rapid validation and adoption of a consistent sampling protocol, confirming the validity of the wastewater analysis, and ensuring potential for generalizability by fully understanding what the samples present. So those are the 3 things: making sure that we understand how to find it, what that means, and can we apply this, across the board. And there's a number of other considerations shown here. And so just going back to that conversation about how do we know that we found it, how do we know that it's all there, you're looking at, again, this is, a lot of this came from the Canadian Water Networks Coalition. And so one thing is the persistence of the genetic signal over time at different temperatures, just like hold times for any other tests that we run. What is the impact on the viral load? And then also, what does that mean per infection? How much virus should you find in the wastewater? And so there's some information out there that very early on, there's a large, essentially, dump of virus, but later on in the infection, it's not quite as high. And so another conversation is about the extraction and concentration method, which I mentioned earlier. Wastewater matrix effects, so pH, if you got ammonia in there, TSS, some of those usual things that we're looking for in wastewater, are they going to destroy that virus? What's the impact? And then, information about the sampling method, the flow rate, how do those affect the quality of the sample? And the population that's connected to that wastewater sample, what's the number like? Do you need a certain number of people to ever be able to hope to find it? And then there's other PCR specific based things, like what is the best additive to use to find the virus and amplify it? And finally, is there anything in there that would inhibit the ability to see the virus? So typically, the PCR technique right now being used for diagnostic testing, we understand that matrix. It's not as complex as a wastewater matrix, where you're adding any variety of items. Just look at the chemicals that we're talking about today in this seminar. And so what will happen to the virus in the presence of those species? And one thing you can do is add this human fecal indicator, what it's called. It's the pepper modal virus. It's essentially in all of our stool. And so that's a way to make sure that you've found something. It hasn't been destroyed. And just to get a bit into the sampling, so this image here is from a CBC News article that came out, I think a few months ago now. Highlighted some of the work being done at the BC CDC, and again through the Canadian Water Network. And Bonnie Henry out here in BC did address this a few months ago and mentioned that they're looking into it. And so what are the protocol? Well, they're asking for a 1 liter sample, unpreserved, 24-hour composite, preferred, cool at 4 to 8 degrees. Nothing new there for our industry. Go to -80 if you want to archive that sample. Keeping sampling data, date, time, sampler, things that we would normally have on a chain of custody. Untreated sample preferred, and definitely a good time to highlight the help of travel and field blanks and making sure you include those. And so I think the good news here is that this is not going to be a major undertaking for any wastewater treatment operators or anyone taking samples. So that's really nice. And so currently the sampling is nice and simple, and I'm going to just get into a few results now. So these are the results from that original publication out of the Netherlands. And so this came through the KWR Water Research Institute, which is run by G. Medema. And what I'm showing you on the right here, this is cases. So this was clinical cases increasing over time in the Netherlands. And so what's interesting here is there's no positive signals in samples taken 3 weeks prior to first reported case. And this is over 6 different wastewater treatment plants that they were testing. So not surprisingly, 3 weeks ahead of time, didn't find anything. Started seeing positive signals 1 week after the first case. And by March 15th, right on the middle of your graph here, all the wastewater treatment plants showed some sign of the SARS-CoV-2 virus in the wastewater. And in fact, 1 sewage sample had a positive signal 6 days prior to the first reported case. Now, that's the interesting part about the technique here is it doesn't necessarily pick up the virus before you would be able to identify infection in a person. It's just that you have to also remember we're not testing everybody. In particular, here in Canada, in certain places, we're not testing asymptomatic individuals. So this gives you a way of sort of looking at an unbiased approach to testing. So some of the other early research was coming out of the States, and there was a group out of Boston who was doing quite a bit of work. And so this is one of their first publications. And so what they're showing here is essentially the amount of virus that you've picked up in blue, so that blue curve, followed by a curve showing the cumulative and daily confirmed cases in orange. So it's interesting that it certainly follows a trend to a point, but I also want to highlight this blue shaded region is essentially showing you the variation from the highest to the lowest result they picked up during that test day. And so that shows you a little bit of the challenges of the test, where it definitely needs some optimization, because you can see there's a wide range of recovery on especially a couple of those days. And so how do you reduce those outliers? And that's what's being worked on now. But interesting to see that it definitely follows the trend of clinically reported cases. And then the other question some people have is, well, what can I do with this data? Can I then, let's say I get a result, can I say that there's 12 infected people in this region or something of that nature? And this is work out of Australia. They've taken it to the level, and I wanted to show this equation here because they're trying to find a way to come up with a reasonable rationale for how you could give the number of infections. And you can see that it's not straightforward. You're looking at RNA copies, which is the PCR test, versus liters of wastewater, grams of feces a person per day, and RNA copies per gram of feces. So now you have to figure out what is the grams that are being deposited, how much RNA is expected in each of those samples. So that's definitely a dirty job, for one way to put it. And there's a lot of information that we don't have there, and we're just kind of what we're seeing is people are doing the best they can with the information they have, and over time they'll develop these equations. And even one thing that I've seen, there's a group out of the States who is essentially just comparing their data to what's being reported in the community, and through a large data set are just trying to build that algorithm that will just allow you to hopefully really narrow down how many cases you would expect based on the results. So there's a few different approaches here, but this is definitely not a completed product yet. And of course, I've had a number of people call after seeing different things in the news asking about whether this testing is available. And there's some interest on the level of identifying infection, but safety is actually one of the first things they ask about. So I just wanted to share this slide. This is from an Alberta Health Services document. And, the good news is the expectation is that contracting COVID through exposure to wastewater is unlikely. And they just suggest standard PPE, standard protocols for sampling wastewater. And, I think one of the things to remember here is that probably should be the case all the time anyways. There's other viruses, there's other things in the water, so I'm sure these practices are being followed. Just a good reminder to make sure you're being diligent. And so that's the general consensus. I think it's worth mentioning, is there any other information out there? And, there is some realities that, maybe we have to consider that there is some possibility of infection. One of the reasons being that was highlighted in this article was that it's difficult to isolate the live virus. And so is the thought that you can't catch it from wastewater because we haven't been able to isolate live virus from the wastewater, or because it's just very difficult to isolate the virus in general? And so that's one thing to consider. Gray water, so that water that's going down the sink and everything, that's not expected to be a major concern. And, they do mention that risk might be expected to be highest in areas with high population, direct exposure to aerosolized wastewater, and regions that lack adequate water collection, treatment, and disinfection. So, I read that and think, well, we're lucky in Canada here that we do have the proper infrastructure to mitigate the risk of this virus to our wastewater operators. And I wanted to throw this slide in here because this is something that I kind of heard about maybe back when we think about SARS-1, if we want to call it that, which definitely I remember found its way to Toronto. And there was some conversation about people contracting this virus in an apartment building, which for anyone who lives in an apartment building, that's a bit concerning. So how this happened and what they've sort of identified, in this case, it was a building in Hong Kong, 321 residents infected, traced back to one person who visited. And in this case, it has to do with the design of the building and the fact that they have floor drains in the bathroom, which over time dried out, and then aerosolized virus was actually passed back up through the pipes. So that is something that I don't think that's prevalent in buildings in North America. So that's one thing to keep in mind. And, they do go into a little bit of detail and say, make sure the drains don't dry out if you have this type of infrastructure. And they're actually investigating a similar report about SARS-CoV-2 in Hong Kong right now. So, I thought we'd address that because it could be concerning and definitely related to wastewater. But I think as long as you don't have this type of structure, and we don't really build we don't have plumbing done this way, so I think we're pretty safe out here. And just looking at that future outlook, so what are we going to do with this test or this technology? And there's a story out of the University of Arizona which got in the news a couple weeks ago now, where they had tested all the students before coming into the residence, but we're also testing the wastewater. And a couple days later, they detected the virus, went back and tested the students and found 2 positive cases. So that's a nice positive example of using this wastewater-based epidemiology to kind of identify the virus before an outbreak occurs. And I think it's worth noting that there is programs going on in many countries: Singapore, China, Spain, Canada, New Zealand. In the US, there's more than 170 wastewater facilities across 37 states that are being tested. And the UK has announced testing at 44 water treatment facilities. And, the Netherlands, who we talked about earlier, has been doing 300 sewage treatment plants. So there's a lot of testing going on. And so this is moving quickly, and, the information just keeps getting better. Future outlook for this technology in the first place. I mean, other diseases, I think hopefully COVID-19 is not here to stay, and we find a way to address this challenge. But I think there's going to be other viruses, and there currently is viruses that we could be monitoring through wastewater. And so that's something that, down the road, now that we've seen the application in the current pandemic, perhaps it moves forward with other viruses. Engagement with local municipalities and health authorities. So one of the biggest pieces right now is that education to the groups who sort of drive forward the types of regulations and testing that we're going to do. And so I've found that the wastewater to this point is kind of a curiosity, and those regulators and those groups aren't pushing for it. So having those types of conversations and making sure we're informed about what the application really is for. And continued method development, of course, there's going to be more work going on. And like I said, there's a lot of people, a lot of great researchers working on it. And understanding the risk in water as a source of infection, making sure that we're safe and we know what we're dealing with. And final slide here, just to say, are you interested in testing? Some things to consider. What do you want to use the information for? Is it trending? Is it, hey, do I have more virus this week than I had last week? Is it going up, down? Do you need a quantitative versus a qualitative result? I realize I put quantitative on here twice, apologize for that. And so, yeah, it's more, do you need a presence absence, or do you need to know exactly how much virus is in that water? Those are going to be two different programs. Cost, the number that I've seen, like I said, there is some groups doing the testing, and based on some other information, I've seen the cost like on a per sample basis. Let's say it's around $200, just to give you an idea. That's always an interesting factor of testing. Of course, if you're going to do a specific project, there probably would be some method development involved, so you need to incorporate that into your budget as well. Sample locations, where are you going to sample? And sharing data, are you willing to share the data that you get? Because I think that's one of the keys right now to really drive this forward, is that sharing of information across different groups so that we can really understand this technique. And so, if anybody has any questions or is interested, I put my email on there and my direct line. I think it's a conversation I'm happy to have with anyone. I have connected with some of the different groups in the Canadian Water Network and some researchers just to see how we fit into the entire equation. And so, yeah, feel free to reach out, and I'm happy to answer any questions if there are any.
Thank you, Brian. Thanks for that. Appreciate that. Does anyone have any questions for Brian? If so, you can type them in the question box on your control panel. Are you seeing demand for testing, Brian, for this?
I'm seeing a lot of questions, but everyone's being asked to look into it. I think I've had a lot of people say, hey, my boss wants to know what this is all about. We're not sure what we want to do with it or if it's going to move forward, but we're just gathering information. So that seems to be the level that it's at right now.
Okay. No questions right now. If you have questions, feel free to reach out to Brian. Thanks again, Brian, and we'll move on to our next presenters.
Thank you.
So next up is Simone Levy with Innotech Alberta and Sheila Luther with Matrix Solutions. Update on sulfur, the old new contaminant. Simone, I'm going to give you control here. Just give me a second. And Simone disappeared.
I should be here.
There you go. It just disappeared on my control panel for a second. Sorry about that. You should have a message on your screen. Okay, at the top of your screen, Simone, there's a box that says display settings.
Yeah.
If you can change that to swap presenter view. Like on your PowerPoint slide, there's a thing that says display settings. Black box. There, oops. There we go. Looks good.
Okay.
Okay, go ahead.
Okay. One moment, I'm just going to turn on my webcam.
Okay, good.
All's working good.
Wonderful. Okay, thanks, Joe. We'll get started. So our presentation is sulfur, the new old contaminant, sort of a re-emerging contaminant. These sulfur blocks have been around for decades in the province, and now that a lot of these facilities are reaching the end of their lives, closure is really the driver. So it's shifted a little bit from a maintenance stage to closure, and there's been some challenges around there. So we'll just do our introductions here, and then we'll get into the slides. So I'm a research scientist with Innotech Alberta. We focus on applied research, testing, innovation, and science-based regulatory support. And I'll be co-presenting with Sheila Luther with Matrix Solutions. I'll let her introduce herself as long as technology cooperates here.
Hello, I believe I'm unmuted. Can you hear me?
Yeah.
Yes. Okay, so my name is Sheila Luther. I'm with Matrix Solutions. I've been working as a consultant in Alberta for over 20 years and have had the opportunity to work on a lot of sulfur affected sites during that time. So just bring that experience to the table, more of a practical experience working with these sites that we wanted to talk about today.
Great. Okay, so in our talk today, we'll talk about sources of elemental sulfur, some of the environmental management guidance, assessment, and remedial strategies, some of the challenges, so why we're actually bringing this to the table in terms of cost, logistics, and closure, and just the fact that you know, those sulfur blocks that that you saw in the first slide, and we'll get into in a moment, you know, just cover such a large area that really making sure that management strategies are nailed down can really have big implications in terms of cost, liability, and the ability to get to closure. So digging into these things a little bit, and then, you know, moving forward to identify strategies that could result in some lower costs, and making sure that remediation is happening because right now it is really a challenge for some companies to be dealing with these sites. So sources of elemental sulfur. I realize it's a bit of a shift away from some of the other emerging contaminants in the talks today. So sulfur is a byproduct of sour gas and oil processing. It's found at these processing facilities throughout Alberta. It was stored in hectare-sized blocks. Like I said, quite a large area that it covered. They were poured right onto native till soil. And again, this has happened through the decades of oil and gas production in Alberta, primarily in the sour gas belt that we'll look at in a moment. There were anywhere, I think the number's around 60 sites in the province that had these blocks. Right now, a lot of them have been removed, the sulfur block itself, and then sent away for overseas use for the most part, and also creation of fertilizer. But we do have these remaining base pads with sulfur present, and those can be a challenge to manage. Other sources of sulfur ongoing, there are huge blocks up in the oil sands processing area, and also at refining sites, and through storage, handling, and transportation sites as it moves to, again, sometimes those overseas markets. So why is it such an issue? So under aerobic conditions, we have oxidation of sulfur in waste and soil and water. And what happens is the sulfur reacts with oxygen, water, and microbes, and converts it to sulfuric acid. And it's really that sulfuric acid that is the problem as opposed to the elemental sulfur itself. So what happens when you have elemental sulfur impact as it starts to oxidize? Well, you get lowered pH as low as 1 to 2, which is really quite drastic. For those of you familiar with managing soils, we have increased electrical conductivity from that sulfate for the most part. And that soluble sulfate then can be released to surface water and groundwater. And in terms of soil health, we have reduced availability of major nutrients, ion exchange and leaching issues, reduced labile calcium, phytotoxic ions, these metals, that becomes an issue for several different things, including plants. We have reduced microorganism activity, except for those little fellows that are responsible for sulfuric acid production. They seem to thrive. And then just, general, so we have a little photo here showing a relatively small patch of impacted area. So oftentimes you get, something like you would see with a salt impact, where you have very limited sort of scrubby vegetation, what can grow, oftentimes bare. We have some of those sulfur base pads that sort of look like a moonscape or something, where there's really, really very little growing, very little that can grow on them. So housekeeping, I guess there are sort of 3 stages of sulfur management. One is active facility, and we do have a number of active facilities right now that aren't really slated for closure, progressive reclamation perhaps, or a remediation certificate for a certain area. But on those active sites, it's something that we'll come back to a couple times through the presentation. It is really important to keep on top of that housekeeping, just to make sure that you don't have the acidification and the sulfate impacts in particular that we've seen that really do extend into the soil profile and really kind of exacerbate the issues that you get in terms of cost associated with remediation and the challenges and logistics and so on. So making sure that we're addressing the problem while it's at surface essentially is really important. So this is a picture from an active site. The coordinator on site said, we have herds of summer students that come out and pick up these sulfur chunks, and you wouldn't know it because they just kind of re-emerge, right? So they just kind of move their way to surface, and they can, result in soil and water quality issues, surface water management challenges, etc. And they're also very friable, so it is hard to, with any kind of mechanical means, to pick them up. One of the things, and Sheila could jump in here if needed, but we see impacts at surface. So let's look at the pH, for example. So this is a profile within one of these sulfur blocks. So we see, really quite low pH at the surface, but it doesn't extend, past about 1.5 meters in depth. So I guess it's relatively close to surface in terms of impact, but it is really important to stay on top of it while it is close to surface. And one of the things that we see is buffering capacity of soils as well. In some of these areas, they are able to buffer themselves for that acidity to an extent, especially once you get down to where there's a little bit more calcium carbonate enrichment. But at surface, you really can get some pretty severe impacts in terms of the sulfur and the sulfate. So we mentioned some of the issues associated with plants and with these soils, the co-contamination issue. So this is actually something that's really quite tricky. So the metals, for example, if you have elevated metals or you have some co-contaminants that came from either processing chemicals or a release or a spill, or those of you that have worked on these sites, you can find some odd things in odd places. When you have those co-contaminants that require landfilling, what it means is that you have to manage, and you have elemental sulfur over 500 milligrams per kilogram, which is quite a low concentration. It becomes sulfur waste and has to be managed as such. And we'll get into some of the implications there going forward in the presentation. But really what it means is that your tipping fee can be 6 times that of a regular tipping fee. And so that's really one of the challenges that licensees face when dealing with these sites. So management guidance, there are several different documents that we have to refer to, and that is some of the challenge, especially for new practitioners, just understanding, in a holistic sort of conceptual site model approach, the soil, surface water, groundwater, different receptors, different guidelines and so on. It can be a bit of a challenge, so I'll just do a brief overview here. So active sites that have sulfur blocks, really preventing widespread impact on and off-site. That's how I started my career, actually, many years ago, was collecting samples around these sulfur blocks. Currently, we have the guidelines for landfill disposal of sulfur waste, remediation of sulfur-containing soil, so quite a comprehensive guide. It can be a challenge for some, especially new practitioners, to interpret some of the guidance there. Another reference is more related to acid rock drainage. So it's not exactly equivalent. I mean, the source can, in both cases, be sulfur, but it is a little bit of a different scenario when you have a pure elemental sulfur versus a complex that then oxidizes. There are different, one of the things that comes through in this MEND manual is that there really are a ton of different test methods for determining potential acid generation of soils and mixtures. So that's for those of you that are lab folks in the audience, that might be something of interest there. And then for site management, there's obviously the Alberta Tier 1, Tier 2, and surface water quality guidelines that need to be adhered to. Within the landfill guideline, there's also reference to TBG and some of the other directives that give guidance on how to manage these sites. So I'm going to turn it over to Sheila to go through site assessment, and then we'll revisit remediation.
Great. So yeah, we'll speak a bit to site assessment strategies in light of all the information that Simone has presented. So this is just reiterating, as we design site assessments, we need to consider not only the elemental sulfur itself, but the breakdown products which relate to the hazard. So we need to look at sulfate, pH as being really important as well, in addition to the elemental sulfur. And then, and obviously soil, electrical conductivity, and other detailed salinity parameters. But as well, we need to look at other co-contaminants that could be present, because often in these sites, these sulfur base pad areas, they may have been used for other purposes at the facilities over the years, and therefore there could be other types of contaminants present. Then a strategy looking at receptor and exposure pathways needs to be considered with these, especially for these older sites. And another factor that I find particularly interesting is that natural and altered mineralogy. So what I find with these sites is that it takes a knowledge not only of one discipline such as soil, but looking at water, geology, ecology, and basically the risk as well. And so it takes kind of a broad view to understand what all is happening. Definitely that geochemistry knowledge it has to come into play. Next. Are you able to advance it, Simone? Yeah, there we go. Yeah, so we use this 3D model just to tell the story a bit about how we are approaching these sites. So I like to think of it as a set of zones, so that zone 1 is where we see acidification just below the source itself, and there can be really unique chemistry happening in that acidified zone in the soil, where the pH can get below 6.5. Typically in these areas, any calcium carbonate that was naturally present has dissipated, and we run the potential of highly acidic conditions. Obviously, no vegetation can be sustained, and potential solubilization of metals. Whereas further out in this zone 2, in the green zone, we see in our Alberta environment that the plume is neutralized due to the naturally present calcite, or otherwise known as calcium carbonate. This results in dissolution. We see dissolution of the calcium, especially in proximity to the acidic conditions, and then precipitation with the sulfate as gypsum. And that results in more of a dilute plume further away from the site, and it results in a plume that can be less than 3 times guideline, versus right at the source, you can have 10 times guideline in the soil and in close proximity. Then we just wanted to mention about some of the receptors that have to be considered. Obviously, the ecological soil contact zone, as well as the domestic use aquifer, should it be present, as well as the surface water receptors, including freshwater, aquatic life, wildlife, livestock watering, irrigation, depending on land use. Next, Simone. Yeah, so this just provides a bit more detail on some of the geochemical reactions that are occurring, but just to focus this on some of the risk and key things happening. Where that sulfate is present just below the source, that's that zone where we see the zone 1 where we see the acidification. In that area, there is potential for mineral dissolution, so increased dissolved metals and acidic conditions. But again, as it precipitates, the calcium carbonate can neutralize that, and we get that precipitation of gypsum. So those are the common reactions happening. We also, in an anaerobic condition, though, have the potential for sulfide minerals to form as well. Next. So we wanted to mention that there and recognize that much work has been done on this issue. I know at the time when I was at U of A in the 90s, there were to that time, there was some work going on sulfur base pad chemistry. So certainly lots of work has been going on this issue historically. And one study that we reference here was incorporating sulfate into potentially the subsoil salinity tool. I believe that effort wasn't pursued in the early after around 2012 when it was being worked on, but this is some of the outcome of that work. This is some model output that just helps to depict, prepared by Equilibrium Environmental, that helps to depict how sulfate behaves in the presence of calcium-rich environments. So when you have a calcium to sulfate ratio of 1 or approximately 1, the sulfate will sort of plateau at a concentration below 2,000 milligrams per liter in a saturated paste. So just to show that that sulfate isn't going to reach tens of thousands of milligrams per liter if there's lots of calcium around, and that's what we often see in these environments. Whereas if there is a shortage of calcium, so there's not much calcium relative to sulfate, you can get really high sulfate concentrations. Next, please. Yeah, and we wanted to also emphasize that the sour gas belt that, like Simone mentioned earlier in the presentation, it corresponds with soil environments that typically do have natural buffering capacity in the Alberta environment. This information, this mapping, was conducted by Holloway-Chuck and Fezenden. It's a classic study in 1987 that looked at the buffering capacity of our soils related to soil sensitivity to acid deposition. But it also is relevant, I think, for these types of base pad areas. We need to recognize that in these areas, a lot of times there will be calcium carbonate enrichment, particularly in the sea horizons and below. And so it's very important to understand that that factor at play when looking at how these areas will weather over time. It is a benefit that most of our natural geology in these areas does give us some buffering to the adverse effects of this contaminant. Next, please. Yeah, so we wanted to speak a little bit into analytical methods and where we see some advances for understanding these environments, particularly advances in accessibility to some more advanced testing. And I will mention that these things we find useful in environments where there's either been historical limestone treatment of sulfur base pad areas, or there's been a sulfur base pad area that's weathered and interacted with the natural calcium carbonate present in the soil, and then we're brought in to do assessment at that time. So these conditions result that we need to understand how the soil has changed through the weathering. So, and our current guidance doesn't go into this level of detail, doesn't really take into account that changes may have happened in the mineralogy over time, and you may have some precipitation of sulfur in gypsum sulfate already. So this just shows in a typical weathered condition where the sulfur base pad has been around for years, perhaps weathering and also treated with limestone, you will see a portion of your total sulfur as gypsum sulfur. Whereas a portion may remain as elemental sulfur, and then another portion would be extractable sulfate sulfur that you would pick up in a saturated paste extract as part of your detailed salinity analysis. And so it's really important to understand all these forms of sulfur in order to design your remedial program. The current guidance suggests it's best to add limestone to treat for total sulfur. However, if a large portion of your total sulfur is in the form of gypsum, it won't benefit from the limestone treatment. So it's helpful to understand this in order to design your remedial program. Other factors at play that are useful to understand include the pH and the soil buffering capacity. So the calcium carbonate equivalent that might be present within the soil profile naturally or through historical limestone amendment is critical to understand as well in order to design and evaluate the risk of the material in place. Next. Yeah, and I also wanted to speak to acid-base accounting. This comes from that manual that Simone was mentioning, and how that might be useful in determining the net acid generating potential of the soils, particularly in light of there being some natural calcium carbonate or historically present limestone amendment material. So a good thing to understand within the soil profile is whether the soil has a net acid generating potential or a net neutralization potential, depending on the zone, be it in zone 1, zone 2, and so on that you're evaluating. So these acid-base accounting testing can be helpful for that. And furthermore, what I really enjoy the output of is the quantitative evaluation of materials by scanning electron microscopy testing, which is now available to us, and it quantifies the form of sulfur when a particular sample, such as elemental sulfur, sulfate, gypsum, sulfide minerals, etc. I recently had a chance to review this type of data that was provided by Saskatchewan Research Council. They have a testing lab that can provide this to industry. There's probably others out there, but this is the lab that provided this output. This particular output is for pyritic soil rather than a soil affected by sulfur or elemental sulfur. However, the output would be similar in either case. So in this case, our main sulfur that is subject to oxidation is pyrite sulfur. So you can see this output from this testing gives a good idea of the percentage of that present in your sample. It will also give you an idea of your gypsum, how much gypsum is present of the total sulfur you're analyzing. And then of interest as well is it'll give you output on your calcite concentration, your calcium carbonate. And in this case, the first 3 samples, they have almost negligible calcite. They've already oxidized and there isn't sufficient natural calcite to prevent acidification. So we're seeing acidification in samples 1 to 3, but sample 4 less so because the calcite is present. So this gives a full picture of the forms of sulfur in the solid phase in the soil and can be very useful for planning future remediation. Next. Yeah, and then we just wanted to talk about some practical considerations. We have found that on some sites, it's very critical to review historical borehole logs if there's a long history of assessment. Sometimes historically buried sulfur layers were not analyzed because they're pure sulfur, just like you would with free product in a sample. We don't always analyze that as well. So it's good to go back and review those logs because that can be important to understand the source. In general, there's a lot of heterogeneity in distribution of sulfur, and the sulfur is quite friable, as Simone mentioned. Typically, approaches include grid sampling. EM surveys can be helpful where there's a sulfate issue. And I guess we typically target areas where sulfur was processed, handled, or stored for this grid sampling. Challenges can be on active sites. There's areas that might not be readily accessible. Next. Yeah, and then an outcome, this is just an example of an outcome of an assessment of a site. It shows also some advanced techniques we can use for plume visualization. In this case, we're showing the sulfate plume. It does not necessarily show the elemental sulfur, but you would find that the elemental sulfur presence will correspond with the very high sulfate concentrations. Our scale shows that the greater than 1,500 milligrams per liter is the dark purple. So this shows, you know, that extensive areas of a site can be affected by that. However, it also shows that the sulfate richness in the deeper zone 2, we call it, cannot be as wide, sometimes is not as widespread as actually the source. And so it's different from say, a chloride plume where we see the chloride move away conservatively. In the case of sulfate, it is reactive, and therefore we can see large reductions in concentrations in close proximity to the source. And that's what we're seeing with this in the 3 dimensions. Yeah, so just wanted to mention that we at Matrix are working on modeling this, taking into account the reactive chemistry in support of some of our client work. Matrix, sorry, go ahead, next slide. And Simone, can you take it over, please?
Sure, and just to cap off what you were saying, Sheila, that we have a follow-up session of presentations around sulfur and large facility liability and environmental management coming up at REMTech in October. So if you want more information, that would be a great venue. Okay, so a little bit of remediation. I have 26 minutes on my clock, so I will try and speed up a little bit here. So we already talked about some of the guidance, the 500 milligrams per kilogram being classified as sulfur waste. So your options are to landfill, and if you have a small quantity, so less than 10 cubes, you can pre-treat with alkaline material and dispose as a regular soil in a class 2 landfill. Large quantity requires encapsulation in alkaline material bunker. And when we are talking about limestone, we're talking about material that needs to be quarried. It is quarried from primarily one location in Alberta, down sort of by Canmore, I think it's Exshaw area, and then it has to be trucked to site, and sometimes they're quite large volumes. So it is something to consider if we're thinking about sort of sustainability approach. In situ land remediation, so Sheila talked a little bit about that. I'll talk a little bit about it as well, how we treat on site. And then land application is an option. I don't think it has ever been used in Matrix history anyhow, but it is an option if you have low concentrations and you have agricultural soils that are sulfur deficient. That is pointed out in the guide as one option. There's also, actually I should mention, another option in the guide around alternative liming products. Some of them can be quite corrosive and challenging to manage logistically and from a health and safety perspective, but that is one thing to think about, is alternative alkalinity sources versus the limestone. When we do lime on site, one of the challenges is that you're addressing that EC, but you are adding some ions, and so getting down to that tier 1 unrestricted land use for meeting salt criteria for the most part is challenging. And so that sort of presents some issues in terms of ability to achieve closure. And then another closure issue is around the dissolved sulfate or the dilute sulfate plume that Sheila showed on her previous slide, how to manage that in the long term. And again, some of that modeling can be helpful there. The limestone amendment, I think I talked a little bit about this. So we're looking at sulfuric acid. We're looking to tie up the hydrogen and tie up the sulfate. So we end up with gypsum, calcium sulfate, water, and CO2, which is great. We do see that sulfur, with its heterogeneity, with its little chunks, can be hard to get the right kind of mixing. It can be hard to mix deeper down in soil. So this is a surface application where it is at surface, but deeper down, you know, if you're looking at some kind of incorporation, rototilling, or even an ex situ amendment and mixing, in some cases that's required. Getting the right ratio is very important. So we talked about this buffering capability that gets taken into account when you're determining your liming ratio that you need. So you subtract for the natural capability of the soil to buffer what hasn't already been used up. Sheila mentioned that understanding what gypsum you have and making sure that that's not included in your ratio of the sulfur that you need to counteract, because that will require you to add more limestone than is needed. The mixing, and then making sure that there's some kind of mixing, because otherwise you can get wash of this limestone material into water and alkalinity, potential alkalinity problems there. On-site remediation, so again, limestone amendment, that's sort of for the most part. And even doing that at surface where you have impacts, we found it can be really important to do that at one site without a lot of proactive management. Impacts changed from 0.6 meters, and that was pH and sulfate to over a meter, and so that really kind of blows up your soil requiring remediation, and at a meter becomes much more difficult to manage in situ or impossible than it might at 0.6. So that proactive remediation being one of the key messages here. Again, you can bring EC down to quite reasonable limits, but not below your tier 1. Sort of somewhat of a challenge. Your pH usually, you can get up to fairly neutral without too much difficulty. The persistence may be an issue where you have to keep monitoring going forward in case you do get that reemergence of sulfur and ongoing generation of sulfuric acid. And I know that bench testing, so we have the ratio, the amendment ratio that's provided by a laboratory, but you can also do some bench testing to make sure that your ratio of limestone is adequate and not overkill. Landfilling procedures, so some of that cost driver has to do with that limestone bunker encapsulation. Only certain landfills, and it's quite a civil engineering and permitting task to be able to create a bunker. There's logistical management as well. If it rains into your bunker, you got a problem. So landfills do find a challenge with managing those bunkers. So some things to potentially look at there to make sure that these sites can be managed cost effectively and also protect landfill operators from acid generating waste, obviously, but in some cases there's a bit of a happy medium that could potentially be struck. And the thing with the bunkering, right, if you don't have really high concentrations, really high potential for acidification, that bunkering really does tie up landfill capacity and create some challenges there. So just something that we're aware of. So last slide, in terms of some recommendations for cost-effective and sustainable and protective assessment remediation strategies, finding that especially new practitioners are coming up with a lot of questions around how to interpret some of the guidance. And like Sheila said, sometimes you need that multidisciplinary team to be able to manage a site on a holistic basis. So some ideas around potentially a companion guidance document or a training course for managing sulfur impacted soil could be something, just because it is quite unique. Potentially looking at the class 2 landfills and looking at some potential like bunkering alternatives, or looking at what is in those landfills, alternative liming products. This closure challenge, creating some consistency, making sure that regulatory communication and justification can be referenced so that sites can move toward true closure. And then this issue of the sulfate in groundwater and surface water, that's something that's emerged since the guideline was put out, and there are some questions around how to manage that. So just wrapping up, if you need to follow up, by all means, we are available. Matrix, again, multidisciplinary team contributed to the presentation, which is great. And there's also a reference list in the presentation if anybody would like to follow up. Thank you very much.
Thanks, Simone and Sheila. Appreciate that. Does anyone have any questions for them? And just a reminder, as Simone mentioned, there will be a stream of 4 talks around this topic at Bremtech in about 3 weeks, so check that out. I don't see any questions. Give me a second. No questions. So if you have questions, please reach out to Simone and Sheila directly. So thank you again, and we'll move on to our last talk of the morning. Matthew Cody with SLR Consulting.
I am here.
Just a second, Matthew. I'll get you control.
Okay. Screen. Let me know when you can see.
Yeah, you'll just need to do the display settings thing. Yep.
Gotcha.
Almost
display settings. So I need to switch the screens.
Matthew's going to be talking to us about the remediation considerations for sites impacted by all this nasty stuff we're talking about. So I'll just turn it over to Matthew. Yeah,
Great.
just click click
Do I
that.
need to swap the presenter view and
Yep.
slide view? Yeah,
Yep,
okay,
that's the one. Yep.
great.
There you
Okay,
go.
great.
Looks good, sounds good.
Excellent. Thanks, Joe. So a big thank you to you, Joe, and the Environmental Services Association of Alberta for the opportunity to present this material. My talk today will be a high-level overview of remediation options and considerations for solid phase media, such as soil and sediment contaminated with PFAS. I'll get to why I'll be focusing on the solid phase in a few slides here. Much of this information is based on projects we've completed here in Western Canada, but some information has also been shared by my colleagues in the US and Australia. So first, a bit of high-level background that will help frame some of the remediation challenges. Move this out of the way here. So PFAS, an abbreviation for per and polyfluorinated substances, are a human-made family of chemicals with the latest count at approximately 4,700 known chemicals. The basic structure of these chemicals includes a tail composed of linear or branched chains of carbon units, where the hydrogen atoms have been replaced by fluorine atoms that is attached to a functional group head. Whereas the head is hydrophilic, the tail is both hydrophobic and lipophobic. It's this unique structure that results in some interesting physiochemical behaviors in the environment. The carbon-fluorine bond is the strongest covalent bond in nature and is ultimately responsible for the persistence of these chemicals in the environment. This bond is also why the destruction of these chemicals is so challenging. For example, Sang et al. Has calculated the destruction temperature for carbon tetrafluoride, which is the most recalcitrant perfluorinated substance, at 1440 degrees Celsius. Some polyfluorinated substances where their carbon chain is not fully fluorinated are capable of transforming through natural degradation processes to smaller PFAS. Let's see if that's going to move for me. Okay, PFAS are also water soluble, and some PFAS are highly mobile in groundwater, especially those short chain PFAS composed of 6 or fewer carbons. There are some examples of PFAS plumes that are many kilometers in length and with little fluctuation in concentration over the length of the plume. So with that, there's potential for some very large site footprints. And some background on our state of knowledge. PFAS environmental science is still in the relatively early stages. Clearly, based on the number of PFAS chemicals, this is a steep hill that needs to be climbed. For example, of the 4,700 or so known chemicals, laboratories currently have standards or lab standards for approximately 30 or so PFAS. So in essence, we may be only getting a snapshot of the PFAS profile at our sites, which is not necessarily inclusive of PFAS precursors that transform to perfluorinated alkyl acids. However, commercial labs are coming out with some exciting tools to address some of these uncertainties, and one such tool is total organic fluorine analysis, also known as TOF, that will allow us to compare the amount of organic fluorine associated with those PFAS for which we have lab standards to the total amount of organic fluorine in a sample, which will really help to quantify the known unknowns of PFAS in a site media. Heather Lord with BVL will be giving a webinar on TOF just after 3 p.m. So that's definitely a webinar you'll want to check out. The science of PFAS toxicity to humans and ecological receptors is rapidly evolving. We currently know that some PFAS contribute to health effects to humans and wildlife, effects including immunological, developmental, and reproductive effects. As pointed out in Lindsay Patterson's earlier presentation, there is a comparatively lower number of toxicity studies for PFAS other than PFOS and PFOA. And obviously, as government regulators depend on toxicology information to formulate environmental criteria, and we're still in the early stages of understanding PFAS impacts, this has presented a challenge for regulators. Currently, we're working with a limited number of criteria relative to the number of PFAS out there. And as Lindsay emphasized, the absence of regulatory criteria for PFAS like PFHXS, 62FTS, PFPEA, and PFHXA needs to be addressed. So for those assessing sites and ultimately planning for the remediation, this presents no small challenge. And just because your soil concentrations are currently below available soil screening criteria, that doesn't mean that'll be the case in the future, as more criteria will be released and some jurisdictions have begun to make existing criteria more stringent. So why is this presentation focusing on solids like soil and sediment as opposed to water? Well, the reasons for this are twofold. First, generally when we're referring to remediation, we are referring to source control. And yes, for many sites, that means both soil and groundwater are contaminated, but with many contaminants, and indeed with PFAS, these chemicals are known to partition to the solid phase to varying degrees. And in soils, and as such, in soils, source areas can act as PFAS reservoirs. And depending on the degree to which the individual chemicals partition to the solid matrix, impacted soils can act as a source of PFAS to the water phase, whether as overland surface water runoff or site groundwater. Thus, part of the strategy for addressing PFAS in downgradient groundwater or downstream receiving environments is to remove PFAS source soils. And second, PFAS treatment science is more advanced for aqueous media. There are currently multiple demonstrated and readily available water treatment technologies out there, most of which are ex situ that do a good job at removing PFAS from water. For many of these technologies, you'll end up with a spent solid phase sorbent material that will ultimately need to be treated. And this presentation will provide some considerations for treating that material as well. Okay, so let's get into it. So clearly, based on the unique behavior of these chemicals and where the science is at, that ultimately means there are some big challenges for those trying to determine the extent of their remediation footprint and selecting the most suitable remedial option. And the most important tool to support remedial planning is a conceptual site model, or CSM. A CSM is a documentation tool updated during each stage of a site's management that captures information on source, the physical and chemical conditions of the site, contaminant transport mechanisms, receptor exposure pathways, and potential receptor effects. I can definitely say that my appreciation for CSMs grew extensively once I began working on PFAS sites. Each of these components of a CSM can go a long way to addressing some of the data gaps or uncertainties previously mentioned. Components of a CSM that you'll want to have nailed down prior to advanced stages of remediation planning include contaminant characterization. You want to understand the extent of your impacts and concentration gradients. Why? Because PFAS remediation is very expensive and surprises on these sites can be extra painful. Also, let's say you're collecting confirmatory sediment samples as part of your program, and considering the long turnaround times for PFAS analytical, you may not have the luxury of having the data in hand before big decisions in the field are made. So you want to have a decent degree of confidence in your planned remediation limits. Understanding your concentrations is important, as some remedial options are better suited for lower concentrations. And then there is the Basel Convention, an international treaty of which Canada is a signatory, which specifies that media with PFOS concentrations above 50 milligrams per kilogram must be treated such that PFOS is destroyed or irreversibly transformed. You should also have an understanding of the PFAS precursors in your soil and where they are located in highest concentrations on your site, as these PFAS will continue to degrade and in many cases will degrade to regulated chemicals. If you don't tackle those areas with abundant PFAS precursors, terminal perfluoroalkyl acids will continue to show up in down gradient waters. In most cases, PFAS may be just one of the contaminant groups present in site media. Co-contaminants can affect treatment effectiveness, both immediately or by competing with PFAS for binding spots on a sorbent, for example, or in the long term, as the degradation of organic contaminants can change soil redox conditions, which could affect PFAS mobility. So you'll want to understand co-contamination and communicate this information to the suppliers of the different remedial technologies to determine if this could affect a remediation program success. Understanding your site characteristics is important, including having a strong grasp of the geology across your site, which includes understanding your soils and the site stratigraphy. PFAS soil interactions are very complex, and it's beneficial to have an understanding of the sorption potential of site soils. It's generally understood that soils with high total organic carbon or high clay content have a higher affinity for sorbing PFAS compared to other soil types. And soil composition may also take some of the remedial options off the table. As we'll see, some technologies aren't that viable for treating silt or clay impacted soils. And understanding site hydrogeology is very important given the mobility of some PFAS. You need to be aware of how water is moving or being confined, as this is important for understanding contaminant receptor pathways that are associated with groundwater or surface water. You need to know which human or ecological receptors are in proximity to your site and where there are potentially complete and significant exposure pathways. And one great tool to help identify those receptors and exposure pathways that are potentially complete is a risk assessment problem formulation. One of the perks with this tool is it will help identify areas of uncertainty, which in turn may lead to additional site assessment work, which will only strengthen your CSM. And so again, why is the CSM so important? As noted on some of the preliminary slides, we're working with some limitations with available federal and provincial guidelines and standards. So I guess theoretically, the safest solution would be to completely remove all of the PFAS from a site. However, given the size of most sites and the remediation costs, that's simply not an economically viable option. And we aren't able to simply wait until the science is at a point where the risks are better understood and where there are abundant screening criteria to better define our remediation boundaries. We know these chemicals do pose an environmental concern, and the footprint of these sites can grow with time. Thus, remediation needs to be prioritized. So how best to proceed? So we can identify a path forward using risk-based decision-making. As depicted on this standard chemical risk component relationship diagram, we definitely have some uncertainties and challenges associated with the contaminant element of the risk relationship. But hopefully, given all the background work we have done to make a strong CSM, we have a pretty strong grasp of how PFAS from our site is coming into contact with human or ecological receptors. By understanding those exposure pathways that are potentially complete and potentially significant, you can then identify a remediation program objective, which should ultimately be eliminating or reducing the significance of potentially complete exposure pathways. Using pathway-specific soil remediation targets, including currently available standards or guidelines, or site-specific criteria developed using tools like soil-to-water partitioning equations, it is possible to define the limits of your remediation footprint. And if your remediation goes according to plan, the results of post-remediation monitoring will show that the exposure pathways have been rendered incomplete or insignificant. I'll now get into summarizing some of the soil remedial options that can be used to manage those potentially complete and significant exposure pathways. This image of a child having to make the daunting decision of choosing perhaps one of the flavored suckers, and hopefully not the yellow one, hugely simplifies the challenge of selecting the most suitable remediation option for a site. But there are numerous options out there, and some have the potential to work well for one site and others not so much, represented by the yellow sucker. I will only be highlighting those remedial options that have been applied in North America and that are demonstrated, meaning those that have been used at sites and where there has been adequate study of the treatment's effectiveness. And while this is clearly a bit subjective, I am largely leaning on those treatment options currently acknowledged as being demonstrated by groups like the Interstate Technology and Regulatory Council, or ITRC. However, there are other options out there, the majority of which are newly developed that have had limited site application and where the effectiveness may or may not have been investigated in peer-reviewed literature. What's missing for many of these technologies is an extensive CV that speaks to their effectiveness at actual contaminated sites. But with time, we should see more options enter the demonstrated technology category. So the first option, thermal treatment, is one of the most widely accepted remedial options. It can be completed both in situ or ex situ. Currently, the ITRC only identifies ex situ thermal treatment as a demonstrated remedial technology, whereas they identify in situ thermal treatment as being a developing solids treatment technology. Ex situ treatment generally involves excavating the soil and transporting to a facility that specializes in the thermal treatment of hazardous waste. The technologies used by the individual facilities vary, but thermal treatment is generally completed in two stages. First, the waste is heated to temperatures above the boiling point of PFAS, and then the volatilized PFAS is sent to an oxidizer that attempts to mineralize the chemicals into their constituent atoms. Temperatures required to achieve mineralization of PFAS referenced in the literature range between 1100 degrees Celsius and 1440 degrees Celsius. The process may also incorporate other chemicals or catalysts to improve the efficacy of mineralization. The treated waste is then disposed of. We're familiar with a few scenarios where the waste is sent to specialized landfills, but also cases where the waste is used in construction materials. So some considerations. The obvious benefit with this option is that the source material is removed from the site, which is an immediate and permanent solution. A drawback of this method is the high costs associated with potentially transporting large volumes of soil great distances. And then the incineration fees themselves aren't cheap. Some ballpark numbers for facilities we have scanned across North America range from less than $100 per metric, Canadian dollars per metric ton, to upwards of $500 per metric ton. Recent study of the emissions being discharged from these facilities has identified that products of incomplete combustion, also known as PICs, may be emitted, either as a result of PFAS not getting fully mineralized or the reforming of fluorinated alkyl chains by difluorocarbene radicals. This is currently priority research for the US EPA, so hopefully in the nearest future, more information will be coming available. Given the concerns over PICs and some high-profile media releases, some facilities are becoming leery with taking on large volumes of PFAS-impacted material. So you'll want to be certain of a facility's acceptance of waste leading up to the remediation date. You should also be aware of how the treated waste is being disposed of, as the final destination might give you some pause. The next option, immobilization. Soil immobilization involves the addition of commercially available soil additives, such as powdered activated carbon, modified clays, or carbon enhanced with aluminum hydroxides, for example. PFAS sorbs the additive as a result of electrostatic or hydrophobic interactions. The proportion of the product added to the soil is dependent upon a number of factors, including concentration, soil type, and remedial objective. But the values reported in the literature generally range from 1 to 10% by weight. The soil is then mixed with the additive and then hydrated and given time to stabilize. Other additives may also be added, including Portland cement or fly ash. These additives have helped to reduce the hydraulic conductivity of the stabilized mass, which means less leachate, and can also improve the strength of the soil from a geotechnical perspective. This mixing can be done in situ, but in situ stabilization is generally understood to be far more expensive than ex situ stabilization, as there are greater challenges with mixing at depth and more sorbent is generally required. Once stabilized, the soil mass can then be placed back into the excavation or located elsewhere, such as an on-site containment cell, or even possibly a landfill, which has been done in the States. Some key considerations for mobilization include this option is readily available in North America. This is a potentially cost-effective solution, though costs are dependent on the product you go with and the proportion of the amendment that is added. The costs presented here represent the extreme range of amendment costs and are not considered of the excavating and mixing fees. The liability remains on site, but you're addressing exposure pathways. Another thought is that perhaps at some point in the future, more proven and cost-effective destructive technologies will be made available. Long-term study of PFAS immobilization is outstanding, including evaluations of how stabilized soil weathers with time. And in consideration of the uncertainties associated with long-term study, this option may be best suited for those sites or areas with low to moderate concentrations of PFAS. With PFAS staying on the site, there will obviously be a condition of long-term groundwater monitoring to evaluate the treatment's effectiveness with time. Also, additives have the potential to affect the soil properties and perhaps even the land use if the material is placed back into the excavation. Concerns have been raised about using additives that increase soil alkalinity, like Portland cement, as the mobility of PFAS has been shown to increase in higher alkalinity ranges. Now on to separation technologies, specifically soil washing. So for this remedial option, I'm throwing my approach of relying on the ITRC's demonstrated technology category of the door. The ITRC does not currently recognize soil washing as a demonstrated technology. The reason I'm including soil washing is it's a technology that my Australian counterparts have been using on a number of sites, and I am also informed that the U.S. Department of Defense has also been employing this technology more recently. So it seems to me that this technology is on the cusp of being demonstrated, and as such is kind of worth including in this presentation. This is an option where both in situ and ex situ approaches have been studied, but I'm under the impression that the ex situ method is more demonstrated. Ex situ washing can be completed both on-site or off-site. The process includes the use of a solvent, commonly water, to separate PFAS from soil into an aqueous phase. Some PFAS readily partition into the water phase, while others may require the use of additives to promote that movement. Once PFAS are separated from soil, physical processes such as microbubbles can be used to concentrate the PFAS. And the aqueous phase is then subject to further treatment, where PFAS are further concentrated and removed from the aqueous phase using materials like granular activated carbon or resins and sent off for incineration. In addition, some systems simply concentrate the PFAS in the aqueous phase, which is then directly incinerated. Considerations for those evaluating this option include, this is a proven technology for other organic contaminants. An application at larger sites in both Australia and the United States has been completed. That said, I cannot comment on how readily available this technology is for application in Western Canada. This is one of the few options that removes the PFAS from the soil with the potential for the soil to be reused. Regarding costs, I sent an email to my colleague Paul Weber, SLR Australia's Land Quality and Remediation Director, asking for some ballpark costs per metric ton, given that he just has overseen a large kind of PFAS soil washing program. And his response was, and I quote, Matt, that's like asking how long is a piece of string. It depends. Cost is hugely dependent upon soil type, PFAS, and co-contaminant concentrations, and the soil quality objective. So clearly not a well thought out question on my end, as cost is dependent on many variables. And then of course, you're left with the treating of the rinsate water, where you're trying to achieve low level concentrations prior to its release back into the environment. And as such, the rinsate may require long-term treatment, which can obviously be costly. Lastly, this technology is best suited for coarser soils as you're trying to break apart the soil molecules to strip off the PFAS. Rinsing fine-grained soils requires much larger volumes of water and has a higher energy demand, and as such is far more costly. For the purposes of this presentation, so I'll get to containment now. For the purposes of this presentation, containment will mean excavating the material and disposal at a hazardous waste landfill, or temporary containment where the soil is excavated and stored on site in an above ground cell surrounded by an impermeable membrane. Offsite disposal of PFAS impacted soil is not a readily available option, though I am familiar with a few facilities that are taking this soil. Offsite landfilling considerations include there's currently a lack of regulatory limits for PFAS disposal in landfills in most of Canada. In BC, while PFAS are not included in the hazardous waste regulations, there are industrial land use standards which can be used for evaluating the landfill option. In many cases, a facility may have developed their own operational thresholds for handling soils with PFAS, so be aware of those. And again, you can't dispose of soil with concentrations of PFOS above 50 milligrams per kilogram as per the Basel Convention. With this option, the liability is transferred to another party, and then who is then responsible for monitoring and possibly treating PFAS for an indefinite amount of time, but something approaching 10 quintillion years when the sun is expected to finally destroy the Earth. This option is costly, especially for those of us here in Western Canada. When considering these facilities, for peace of mind, you should ask for a description of the facility's design and environmental processes. For example, is it lined? Do they have a leachate collection system? How is the leachate treated? And how are they monitoring for PFAS in groundwater or runoff that may be getting discharged from the facility? On-site containment considerations include, it's ultimately not really a super great long-term option, as impermeable barriers are subject to weathering. And with water penetration, there is a potential for leachate issues down the road. However, in the event of a spill, or on-site containment can work in a snap and can definitely go a long way to reducing the footprint of a site. This option is also putting off the treatment of the soil, which may not be a bad thing, as effective, less expensive solutions could be coming online in the future. And with this option, regular inspection of cells and sampling leachate and adjacent surface water or groundwater should be considered. So those are the main demonstrated PFAS remediation technologies for solids. However, as previously mentioned, PFAS remediation science is rapidly expanding. If you're interested in what bench scale and field scale trials are currently being conducted in North America by leading PFAS researchers, you can view product summaries on the US Department of Defense's Strategic Environmental Research and Development Program website. And here in Canada, the Royal Military College is leading some very promising research too, so explore their resources as well. So a few final thoughts. When designing a remediation program or evaluating remedial options, there are a number of factors that will come into the decision-making process, including but not limited to site characteristics, contaminant receptor exposure pathways, the proponent's risk tolerance, and of course, available funding. The footprint of PFAS sites can be large, but through the remediation of source areas, you'll not only be able to reduce the PFAS load in site soils, but you'll be able to reduce PFAS concentrations in groundwater and down gradient surface water. And by remediating soils within the limits you have identified, the project should achieve the objectives of the remediation program, which is to eliminate or reduce the risks associated with potentially complete or significant exposure pathways. As you're working through site assessment stages, you should be updating a CSM as you go, in the back of your head, thinking of all those pieces of information necessary for designing a well thought out remedial options analysis. And when you're evaluating options for your site, you should understand the uncertainties associated with those technologies that are not yet in the demonstrated stage. That said, all options, including demonstrated ones, have their drawbacks and uncertainties. None are perfect. If you're looking into on-site treatment options, then you should plan for bench scale testing, where you're actually using material from the site to not only determine if this option is suitable or to select the best option, but on how you can optimize those options that you go with in the end. And lastly, for those out there that are handling products with PFAS, given the headache of remediating these sites, a good spill prevention plan and having emergency response procedures in place is crucial. If a spill does occur, it's important to get that material out of the ground as quickly as possible and onto impermeable liners and covers, as the footprint of contamination can quickly grow. So that brings me to the end of my talk. I hope that I've given those that kind of are currently involved with or soon to be involved with PFAS remediation some food for thought. If there are any questions, I can do my best to answer those now, or you can contact me at a later point to discuss. Thank you.
Thanks, Matt. Appreciate that. Any questions for Matt? While I give a couple minutes here for see if any questions pop up. So when we're done this morning session, you'll need to just log out and then log in to the afternoon session through a link you should have received. If you haven't received it, drop me an email and I will resend it to you. Matt, it doesn't look like there's any. Oh, wait. What is the effect of soil washing on soil physical properties, texture, structure?
That's a great question. I can't answer that question. I think it's all very site specific and soil specific. Yeah, that's something that kind of one would have to kind of, if their consideration is being given to that option, I think that's definitely a big concern that you could affect soil properties and ultimately the potentially even the land use. So that's a concern one would really want to evaluate.
Okay. Thanks again, Matt. Thanks to all of our morning speakers, and thank you to everyone for your attention and patience. We ran a little late, but we will restart in about a half hour at 12:30. So thank you, and we'll see you a little later.